Wonderful, wonderful. This is my great fear as a professor. Okay, so welcome to the 40 hand object interaction workshop. And so we're going to get started, and I'm just going to have very, very brief opening remarks. It just explains how this workshop's going to work. One thing I want to mention is that a large number of the organizers unfortunately couldn't make it here because of visa issues. So you're seeing me, and the credit for organizing this great event should not go to me. It should go to a number of people who I can see on Zoom who were unable to come due to visa issues. So this is very unfortunate, and they've done a lot of really hard work and recruited a lot of really amazing speakers. And so the credit should really go to them. And so I get to introduce this, and it's a great pleasure. And it's a great pleasure to introduce the speakers, but it's the credit for all this great work really belongs to a number of people, many of whom can't be here. So I'm actually not going to have very many opening remarks because I'd rather just get started to the actual sort of main event that people come for. And so, but just give you a sense of the schedule. We have the HOI challenge results. Hold on, let me see if I can move this. Then we have winner talks, and then we have a series of events from our presentations from a number of really interesting speakers. We're going to talk about all sorts of different aspects of hand-object interaction. And one thing in the middle that we have, which is very exciting, is in addition to the famous people who you have heard of, we have many people who will be famous. And so we have a number of student talks, which is also very exciting. And so I think this will be a very fun event. And we'll be trying to monitor, for those on Zoom, we'll be trying to monitor chat. It would be helpful if you don't unmute and ask questions in the middle of the talk, but we'll try to monitor the chat so that if you have questions, we can participate. So we'll try to do our best. And if there are any technical glitches, just please do let us know in the chat. So we're going to do our best, but technical glitches do happen with Zoom. And so without further ado, I'm going to switch over the computer back to the one that we're using for a presentation for the Zoom folks. Let's see. There. All right. Let's see. And so the person who should be presenting the challenges should be able to. Are you able to share your screen?
Yeah, let me share my screen. Actually, I just changed the host to the local laptop. Is that working well?
Yeah, I think that's working totally fine. So if you can share your screen,
okay,
that's
great.
Perfect. Let's just make sure. Oh, we got
my screen.
Back. Now I got your. Now, yes, yeah. Now, yep. Now we have it, and we're not reading your email, which is always a fear. All right, and so if you hold on for 1 second. What I'm going to try to do is I'm going to try to, unfortunately, the audio, we were told by the previous workshop, the audio doesn't work. And so doing the classic wonderful thing of putting the microphone next to the computer. And so, let's see, how do you increase the volume on Macs? Sorry, I use Windows. It's terrible. Oh, there you go. Yeah, there we go. Let's see if this works. So can you say something?
Yeah. Is it working well?
Can you hear it in the back? Excellent. Let me move it closer. Keep on talking. Okay,
great. So, I mean, if everything is working well, yeah. If the back audience can also hear me.
Okay, good. As you can tell, this may be a computer conference or something else. It feels, we get technology. So, but so long, and we'll be monitoring the chat in case something goes wrong. So please take it away from here.
Okay, great. Thank you so much for UA's help. Yeah, it's a bit unfortunate, like we cannot be there in person to like share all these things with you like face to face. So, but still, I would like to take this opportunity to like introduce a little bit about this workshop and also the challenges we have prepared. So as like you just mentioned, we will have this challenge introduced at the very beginning with some of the winner talks followed by that. And then we will have like excellent keynote talks mixed with student talks. Hopefully this half-day workshop can provide you like all the like interesting informations you are expecting. Actually, maybe I should turn my video on so that you can also see my face. I'm not sure whether it's working well, but okay, yeah. So it's
Yeah,
like
we can see you.
4 a.m. Okay, it's 4 a.m. At my time zone right now, but so but anyway, it's like a yeah, I should take my time. So this is like the opportunity for me to introduce HI40 challenge. So I will start from introducing some of the like data set side and also the challenge tracks we have prepared this year, and as well as the participants and results. That's the roughly the agenda from my side. Okay, so let's start from the data set aspect. So when we're thinking about trying to understand human-object interaction, especially from an egocentric aspect, data always comes at the first place. So we need to have large-scale, like 4D data set describing how human hand interact with various objects, covering both the labels on semantics, poses, physics, actions, intentions, and so on. So this is kind of the motivation for us to like start curating a large scale data sets, which can really describe all these phenomena. And that's why we presented this data set for like 40 egocentric category level human object interaction in last year's CVPR. So we introduced HI40 data sets. It's like a large scale data sets describing humans interaction with objects on the category level. So that is to say, we describes the interactions for objects from the same category with object variations. And this is also to see how people can vary their interaction patterns when the geometry changes. So this data sets is quite different from previous ones in that it contains like very rich annotations in the 4D space. So we have the action annotations describing the human's action label for every single RGBD frame. So this is like an RGBD video data set. So every single frame has an action label. And we also equip the like motion segmentation information with every single frame, describing the hands, the objects being manipulated, and there will be 3D hand poses as well as category level object poses, especially for articulated objects where the manipulation could be pretty kind of interesting. We have this kind of part level, category level poses kind of annotated. And we also have panoptic segmentation in the 4D space for every single frame, including both the object hands as well as the theme backgrounds. Because this data set is captured in natural scenes rather than like on the tabletop setting. So that's why this panoptic segmentation information could be helpful. And we reconstruct object meshes so that like if people want to analyze instant level poses, they can still use this information. So here is like a more kind of comprehensive list for the kind of annotations we have. Apart from what I just mentioned, we also have the camera poses for every single frames. And you can use that information to kind of like understand how to do dynamic camera relocalization. And okay, so there are 3 key features for this data set. One is category level, as I just mentioned. It's not just interacting with a single object from all different categories. So we have like maybe hundreds of object instances from the same instance category. Sorry, from the same category. So you'll see you have this toy car category with all different models with different geometry. So that is pretty important if people want to analyze how this HLI understanding could generalize beyond a single instance. And the second feature is, as I mentioned, large scale. We have like over 4,000 videos containing 2.4 million RGBD frames. And there are like 800 object instances from 16 categories. Some of them are rigid categories. Some of them are articulated categories with more interesting manipulation patterns. And we also, different from previous works, we capture these things in natural, real, like indoor rooms. We have like 610 different rooms in total. We have then 43 semantic categories in these 40 scenes, which is pretty interesting if we want to analyze the semantics in the dynamic scenario. And we annotate very fine-grained action labels as shown on the right. So you'll see some of these action labels, they are really kind of manipulation actions. So in the end, we kind of have this data set covering 92 tasks in total. Some of them are pick and place, but more are functional based tasks. For example, open a laptop or like open the drawer or something like that. So this is about that feature. So this is probably the most most important difference from previous works. This data set cares about functional manipulation. So as some examples shown here, these actions, they are useful. And if you want a robot to imitate human beings to do something, so it's better to understand how humans does this job in a functional purpose. So this is about the data capturing system. I think I would just like briefly mention we have two RGB camera sensors, one Keynote, one RealSense. So if you care about how to transfer information across different depth sensor domains, this is also a good data set to do that. And as I just mentioned, with this kind of HOI data, people are able to learn robot dexterous manipulation from human demonstrations. And also, if you want to synthesis very realistic hand object manipulation for unseen novel 3D objects, this kind of large scale HOI data sets can also help you to do that. Okay, so that is about the data set part. I'm taking too much time. Like the main topic is about the challenge based upon the HOI 4D data sets. We set up two different tracks for this year's challenge. One is 4D action segmentation track. So given some point cloud videos, the participants needs to like assign an action label for every single frame as shown here. So you not only need to understand what is going on, but you need to have this kind of temporal segmentation clearly done on point cloud videos. So that is why it's called 4D action segmentation. The training set contains 2,971 point cloud video clips and 150 frames per clip. So we have like around 2,000 points per frame, and there are 19 action labels to demonstrate you are really able to understand the fine-grained action classes. So as the test site, we provide just the video clips without the labels. So the starter code has been provided at this GitHub link. So the participants need to solve this task. And the second track is about 4D semantic segmentation. Still given some point cloud videos. Here, the RGB video is just for reference, but the participants, they are only able to get access to the point cloud video. They need to segment out like every single points from that point cloud video to trying to associate a semantic label with the points. So the training set is quite similar to the previous one, but now we provide 4,000 points per frame, and like 49 semantic labels are included, covering both the kind of hands, the objects, as well as the background classes. So again, we provide starter code for the participants to start easily. Okay, so as an evaluation, we use frame-wise accuracy as well as semantic segmental added distance and segmental F1 score for the action segmentation track. And worth to mention, we use the frame-wise accuracy as the metric for ranking all the submissions. And then for the segmentation track, we use mean intersection over union as the evaluation metric. Let's see what are the participants and the results. So the challenge has been for 4 months, and we have 10 teams in total submitting their results. 6 teams have outperformed previous state-of-the-art methods. For the 4D action segmentation track, we see the previous state-of-the-art only achieves an accuracy of 77. And now the winner reaches 85. That is like a very huge boost compared with the previous SOTA. And for the 4D semantic segmentation track, very similarly, previous state-of-the-art only has an mean IOU of 41, and now the winner reaches 48. So it's definitely seeing our participants, they are kind of very great at trying to improve the baselines. So this is about the participants for the 4D action segmentation track, the first, second, and third place for that for this track. So I'm listing their method names, their team members, as well as the team affiliations. I'm not going to read through all this information, but hopefully I just want to acknowledge all the contributions from the teams participating in the challenge. So, and today we also invite the winner for each track to share their kind of methods. So especially we have this kind of DPMix, which will be the first spotlight talk after my presentation. And for the semantic segmentation track, this is about the first place. We have actually 3 teams participating in the 4D semantic segmentation track. But unfortunately, the other two teams, they are not really outperforming the baseline methods. So that's why we only have the first place shown here. So Ying will also share their work on 4D and object interaction semantic segmentation, the enhanced point transformer V2. Okay, so with all that, I would just like to conclude my introduction, and I will then let the kind of presenter Yue Zhang to take my place to share their work on DPMix for 4D action segmentation. So Yue, are you there?
Yeah, I'm here.
Great, let me start sharing my screen so that you can take it from there.
Okay, I will share my screen now.
And we can see it on our end.
Okay, thank you. Hi, everyone. This is Zhang Yue. I'm currently a PhD student of Zhejiang University. I'd like to thank all the organizers for putting this amazing challenge and the amazing workshop together. It's a great pleasure for me to share my work here. I'm presenting our method called DPMix, mixture of depth and point cloud video experts for 4D action segmentation. Here are our team members. Basically, my presentation is divided into 3 parts. First, I will overview the 4D action segmentation task, then the analysis of the dataset. Finally, I will introduce the motivation and show the DPMix method we used and give the result analysis. Okay, let's briefly review the 4D action segmentation task in this challenge. In this task, we need to give each frame in the point cloud video an action category label. In other words, the input is a set of point cloud videos and the output is the action described in each frame in each video. The data provided for action segmentation task includes 3,863 point cloud videos. Each video consists 150 frames and in each frame there are 2,048 points with XYZ coordinates but without RGB information. We found that the training dataset has issue of class imbalance. Certain classes have a much larger number of symbols compared to others. Classes imbalance can pose challenges during the training process, as the model may become biased towards majority classes, leading to poor performance on minority classes. Therefore, we employed data augmentation, including flipping, jittering, and scaling. In particular, we applied the CutMix data augmentation method to the images. Next is the motivation of our method. The point cloud value modeling methods can make full use of the geometric information and have a better understanding of the shape and appearance. However, as a relatively new research area, the point cloud value methods might not be good at the temporal modeling, especially for long point cloud values. The traditional value understanding methods have been well developed. Their effectiveness on temporal modeling have been widely verified on many large-scale value datasets. Based on the above considerations, we designed the DPMix method, which fills the depth and the point cloud value methods. We also employ the P4 transformer and the point primate transformer because they have improved effective on-point cloud video modeling. In addition, we transformed the input point cloud videos into depth videos. Specifically, for each point, we projected the coordinates XY onto the pixel coordinates UV of an image. and the coordinate say of the point is regarded as the depth information of the corresponding pixel. Then we adopt several traditional video modeling methods, such as 3D convolution networks, 3D plus 1D mixed convolution, and slew-fast. Finally, we perform the late collaboration by averaging the results from depth experts and the point cloud experts. Here we present the main experimental results and analyze. The submission results on the test dataset indicate that on accuracy metric, the depth value experts outperform the point cloud value experts. However, in terms of the edit distance metric, the point cloud value experts achieve better performance. The possible reason could be that the transformer architecture, each point region performs attention with all the other point regions. However, in the convolutional approaches, the temporal convolutional kernel is typically not very large due to the computational constraints, resulting in the poor cognitive performance in long sequences. So we attempted to increase the temporal convolutional kernel size to extract long-term features. We observed some improvement in the edit metric. However, it still didn't surpass the performance of the point cloud method. As expected, our DPMix method achieved a significant performance improvement in the field of depth and point cloud methods. Furthermore, for each method, we compare the accuracy on each action category. First, we observe that the traditional methods perform better at motion capture. For categories such as grasp, push, and press, where the performance of the P4 transformer was initially poor, there was a significant improvement of the depth value experts. Second, we found that the data augmentation of the images can improve the performance of the depth models. We further counted the misclassified action categories, hoping to provide inspiration for subsequent improvement methods. We found actions between adjacent frames in a video are often misclassified. In addition, the categories with similar action meanings are often misjudged with each other. For example, the category 0, which means the action rest, and the category 6 means the action stop, are often misjudged. Finally, I will make a short summary. Point cloud value experts are good at capturing. Oh, sorry. Oh, sorry, I will make a short summary. Point cloud video experts are good at capturing geometric information, and the depth experts are good at capturing the motion information. Our proposed method, named DPMix, achieves significant performance improvements by fusing depth and the point cloud methods. Okay, thanks for listening.
Well, thank you, Yue, for our presentation. So we will then have the next winner talk from Ying. Are you here?
Yes, let me share my screen first. Can you see my screen now?
Yes.
Okay. Hello, everyone. I'm Xing from the Chinese University of Hong Kong, Shenzhen. And on behalf of our team, I will introduce our work, which is titled 4D hand-object interaction semantic segmentation via enhanced point transformer V2. And my speech consists of the 3 perspectives. And since the background
Oh,
is
sorry,
introduced,
Ying, I think we're not seeing the right screen. So we're just seeing
sorry.
the first slide. Yeah. And it's not in the
Um,
presentation mode. Do you want to go into the presentation mode?
Let me try again. Can you see it now?
Yes, yes.
Yep.
Yeah. Okay. Since the background is introduced before by Professor Yi, so I'll just skip this part. And we use and for the method we use the point transformer V2 as our backbone, and the point transformer is a strong backbone which can deal with downstream tasks like the classification, part segmentation, and the semantic segmentation, which is a task of this track. And here is the detail of the point transformer V2. It uses a grouped vector attention and the grid pooling strategy to improve its performance by the point transformer. And for the grouped vector attention, it enables efficient information exchange within and among attention groups, which can improve the ability a lot. And here is the network architecture in details. It consists of the GVA block and the grid down and up blocks, and the pool and the MLP layers. And specifically, it's exploiting the UNet structure and contains 4 encoder layers and decoder layers. And the specific parameters of the encoder depth and the number of channels and the number of neighboring samples are shown here. And for the data processing, it uses vocalization, and we exploit the grid sampling to downsample the input point cloud with voxel size of 0.02 meters, which is used to reduce the computational burden. And for the data augmentation, we use Mix3D, which makes the 2 things together, and it can increase the generalization beyond the contextual priors of the training scenes and improve the predictions for rare events not captured by the training data. And since we discovered that some categories like the ground and the table has a large amount of the data, while others like the sensors and the box only just consist of a small part of the overall data. Therefore, we combine the cross entropy loss with the lowest softmax loss to deal with the unbalanced data problem. And here is the training details. And also we tried some ways to combine the temporal information, but the optimal way is still the single frame input until the deadline of the challenge. Since the data is very large, we only train it for 10 epochs for about 4 days on 8 A100 GPUs. And we use Adam W as the optimizer and the 1 cycle RL as the scheduler. And here is the result for this method. It is about 7 points higher than the PBTR. And here is the details for all the categories in the test state. And for the further utilization, we use a trained model to extract the segmentation features, which to help the action segmentation track achieve the better accuracy. And the results with the segmentation features are shown here. And here is the information of our lab. And thank you for listening.
Yeah, thank you. Thank you so much, Ying. Yeah, I think that's all for the kind of two challenge winner talks. And after that, we will have very excellent keynote talks. I think maybe Yue, you can take the ball from there.
Yeah, so I'll be taking it. So if we hold on once, so Jitendra is here. So for those who are just joining, this is a hybrid event. So please be patient as we deal with technical stuff. And the area, yeah, you should be able to join on Zoom, and I'll just move stuff around. And then also to add to fun, the audio apparently doesn't work. Hence the very low budget microphone next to the laptop. So your patience is very much appreciated. So if you're
my laptop,
directly use the HDMI or the caption.
I can use an HDMI, that's fine. Okay, and then share screen. Actually worked.
And if you can avoid, limit the number of feedback events to like 2 or 3, I think this will be a great success.
I think we're in the rehearsal view.
And so for those on Zoom, can you confirm that you can hear us?
I can hear, but I think we're in the rehearsal view. It's just not the right view. It's kind of try to like
Oh, wait, no, it's, oh, you.
No, that's fine. It's showing correctly.
It's showing there, and then it's sharing I think the Zoom people are saying the wrong one.
So what do I do?
So if you go to scroll.
Do I do swap displays? No.
No, so I think if you go back, if you scroll down to the share screen option inside Zoom,
Okay.
or scroll.
Okay. So,
However you get to.
okay, let me end show here.
Do I need to stop first?
Okay.
All right, and then actually, if you then stop the share right there, and then share screen. I think it's because it's shared an app, and so it decided to. Maybe you do desktop 1, and then that should actually work. If you share desktop 1, and then you
This mode.
this should work, and yeah, I think that if you hit share.
Okay, both places now.
All right, working both places.
Okay.
Excellent. So
In between I'll have to switch PowerPoint deck, but anyway, it's fine.
Okay.
We'll figure it out.
yes.
Okay.
So Jitendra is someone who really doesn't need an introduction in this community, but I'll attempt to do a very brief one. He's a professor at UC Berkeley, also working at Meta. He has won many accolades. We all use his research. He and his group and his students have worked on nearly every problem in the field, and he has won 5 Test of Time awards, which is a very impressive amount. And so he always has very interesting things to say, and it's a great pleasure to have him here to talk to us about hands and objects. So please take it away.
Thank you, David. So we have half an hour, right? Yeah. Just
I
tell
believe
me
so.
like
I
10
will-
minutes before the
I
end.
will vaudeville hook.
Okay.
Yes, half an hour, yes.
Okay, hands and objects. Okay, that's the title of this workshop. But let me, I'm going to prioritize the audience in the room, even though, of course, the slides can be seen by everyone in Zoom land. So this sets up the problem for me, which is that someday we want robots to be able to do all the things that we can do. And here's a set of actions that are common in a kitchen. And humans can use their hands for this, and robots can't. And a big bottleneck for that is dexterous manipulation. The ability to use our hands, which have several characteristics. They are multi-fingered hands. They have various kinds of sensing, touch sensing, and of course we have vision. And somehow we can solve a wide variety of these problems. And this requires major advances in robotics. So it involves advances in robotic hardware, robotic sensing, but also in learning strategies. And there are two families of learning strategies which are appropriate here. One is reinforcement learning, which is learning by trial and error. And the second is imitation learning from examples of humans doing the task. And in my talk, I will try to do both, but I will start with the reinforcement learning one. And if I don't get time, I may not finish the imitation learning part. So that's the setup. So I'm going to take it through whereby one canonical task that we picked, which is representative of these various kitchen tasks. And what we tried to do was to take it through and see how to solve this task using a multi-fingered hand, which might have tactile sensing and with the use of vision. And this is representative. I'm not saying that this is the only task we can do, but if we understand this one well, we will be able to do others. Okay. So I think the audio is probably, let me play it, because the audio is interesting. So what you see here is a multi-fingered hand. It's a four-fingered hand, and it is rotating an object about the z-axis. The z-axis is vertical in the direction of gravity. And let me show you the annotation here. So it's very important to show generalization. I mean, just like in computer vision, major progress was made when we said that recognition is about generalization. In many robotics tasks, they are quite happy to do it for one specific object. My point here is to show that it should really be generalization in the same sense that we do for, recognizing cats or chairs. So here there is an object, and the object can be of varying shapes and sizes. And all that information is there on the top of the window. And this is about rotation about the z-axis. And there's a weight of the object. Okay, now you should be able to see this, that we are able to rotate objects of quite varying mass and quite varying aspect ratio. And of course, they have different characteristics on friction and deformability and so on and so forth. More examples. So this is what I would recommend you look for in any robotics task. What's the generalization? Okay, so how do we achieve this? Okay, so a major paradigm for this is about doing training in simulation and then transferring to real. Why is this necessary? Because reinforcement learning has high sample complexity, and doing reinforcement learning in the real world is therefore not very feasible. You can, however, do it in simulation, because we have very good simulators now which capture the physics, and you can import a robot hand there and so on and so forth. There will be the challenge that the parameters that you have in simulation will not match what is there in reality. And we have to find a way of dealing with that. So I'll get into that. So we are training in reinforcement learning, and basically think of it as just trial and error. You're going to try various policies. And a policy, what it does is, that's what is shown here. There's base policy module, which is some neural network, which is given the current set of observations, and it spits out an action. And the action here is the joint angles of the various for the hand. And you feed these then to a low-level PD controller, which then tries to enforce that. So how do we train? Reinforcement learning is essentially the same as optimal control for classical control theorists. You have some cost function and you figure out how to minimize it by trial and error. So the natural cost function here is something like you want to minimize energy, you want to be energetically efficient, and that you want to rotate the object so that omega dot k is essentially saying that the rotation axis should be the z-axis. And then you want to rotate at as high a speed as possible, so long as it is up to R max. So that's a fairly straightforward reward. And now, by trial and error, initially what will happen is that the object will actually drop when the hand tries to rotate this. But after a while, it will start to essentially find gates. So this is quite cool. We have done work previously on walking, where the gates are legs walking on the ground. Here it's gates of the fingers twirling the object. How do we train this? Okay, so to train this, it turns out that if the physical parameters are different, if the object is light or heavy, if it has big mass, a big object or a small object, you need to do different things. So, so that makes the training hard, because the training has to work in all these different conditions, right? The policy has to work in all these different conditions. So how do we make sure of that? So there is an idea which is that of using privileged information. So in simulation, you can generate objects of differing mass, differing shapes and sizes and so forth. And that's what is shown in the left in that block. This is what we call privileged information. This is information available at simulation time, but it's not going to be available in the real world. Now you take that and you actually don't care about all those 20 parameters. You care about some 5 of these or 8 of these which actually affect your actions. So that compression is done through this object property encoder, which is compressing it down to this z, which is this latent variable. And then the policy is trained with z as an argument. Okay. And then you output actions. So the actions here are a sub t, and the action you should think of as desired joint angles. So the top row is what we do in simulation. Now we have this problem that if we want to take this policy and run it in the real world, it's not going to run, because in the real world, you won't know this z, because you won't know the mass, you won't know the shape of the object, etc., etc. So you need to find some way of estimating these parameters, but estimating all these parameters is hard. Okay. So what we do is we try to estimate the z, which is this latent variable, which is low dimensional, 5-dimensional, 8-dimensional, something like that. And the secret for how to estimate this is you apply your policy, and as you are turning the object, the way it reacts in your hand reveals something about the object's characteristics. So if you have this past trajectory, and the trajectory here is the proprioceptive trajectory, the trajectory of the joint angles of all the fingers and so on and so forth. Because the system that I'm describing right now is blind. It makes no use of computer vision, and the fingers of the hand have no touch sensing on them. Okay, but you have proprioception, you have all the joint angles. And this previous history is what is shown by this xt minus 1 to xt minus 30 and at minus 1 to at minus 30. So the past state and action history. With that, the so-called adaptation module can estimate this latent state of this particular object which is being manipulated by the fingers. And we can train this also in simulation by just solving a regression problem, that because the z can be the true value of z is given by access to the privileged information, and we build an estimator of it based on the past history. And that's how we train this policy. Okay, so now finally you have a system which can be deployed in the real world. So this is our solution to the sim to real problem. The sim to real problem has been addressed in a couple of different ways, but one popular one is called domain randomization. It was popularized by the OpenAI people. I think it's the wrong way to do it. Why is it the wrong way? Because domain randomization is that you build a policy which is robust and which will work for all the different choices of the parameters. That will lead to suboptimal results. What we want instead is an adaptive policy, not a robust policy. So the adaptive policy estimates these parameters, rather the reduced version captured in the Z, based on the spatial, the temporal history, and then it uses that to determine what action to perform. Okay. So now, so that's the big idea, and this is a paper which was published last year at Coral, and you can read that. And the beautiful thing about reinforcement learning as opposed to imitation learning is, in reinforcement learning, solutions can emerge which we have not even thought of. In imitation learning, we are kind of stuck with all the solutions that previous humans have found, and then we'll just copy them or some composition of them. But in reinforcement learning, new like various kinds of gates emerge and so on. And this slide gives you a flavor of what's going on underneath the hood. We are going to be, the hand is rotating these different objects. And what you will find is that this Z, this latent variable, which somehow encodes some aspect of the object being rotated, is being estimated in real time. And it turns out to be two of those dimensions are shown here. So it's a, let's say, a 5-dimensional variable, a state vector, 5-dimensional Z, and two of those are shown here. And what you saw were that for different objects, you get different values of these. Okay. So now let me critique what we just saw. I showed you rotation about the Z-axis. It turns out that rotation about the Z-axis is an easier one than rotating about other arbitrary axes. So our first line of work was to show that we could do rotation about an arbitrary axis. And then we found that we could not do it the way the program of research that I just outlined. And what we found instead was that sensing is necessary. So in my group, we have previously worked on walking. And we found that you can make a robot walk blind. I mean, after all, humans can walk blind. But there are certain settings in which blind walking doesn't work. For example, going upstairs, going up on stepping stools, and so on. So at those more difficult conditions, sensing is necessary. So the work that I'm going to show you now shows that when we try to do more difficult rotation tasks, then it turns out that the sensing is actually necessary. And we got this beautiful result that both vision and touch are helpful. And we'll even see it quantitatively, that the gap is made up of by half by vision and half by touch. And it's my belief that even though this is one task, this is paradigmatic for all of dexterous manipulation in robotics. Dexterous manipulation in robotics will only succeed when we find proper ways of using vision and touch. So let me explain that further. So we have the earlier part of this talk showed you generalization to different objects using proprioception, but the rotation was only about the Z-axis. Okay. So how do we get general in-hand rotation? So just to explain the problem, we want to rotate about arbitrary. So this is, if you remember your physics, your ijk vectors, which are unit vectors along x, y, and z axes. I mean, the k case we had already done, but we want to do the general one. And then, of course, if you can do these, you should be able to do an arbitrary omega. Okay, and we'll show that. So that's our objective. And the other thing to note is that on the fingertips here is a tactile sensor. And this tactile sensor is comes from a line of tradition called gel sight, which was developed by Ted Edelson at MIT some years ago. And there's a company which markets that. And there are variants of that which have been developed at Meta and so on. But the main thing to know is that on the fingertip, you have some kind of a membrane, and then inside, what you have is some light source and a camera which captures the image. So when somebody presses on that finger, that membrane deforms, and that deformation results in a different image which is captured. So Ted Edelson is a vision researcher, so he basically converted touch to a vision problem by putting a camera inside the finger. There are other technologies, right, based on magnetic stuff and capacitive and so on, but this is the technology we are going with for now. Okay, so that's a good. I also want to point out that rotating an object with your fingers is harder than rotating it in the palm. Again, some demos try to show and put an object in the palm, because once you do it in the palm, then it won't fall down. But rotating in the fingers is more tricky. So, okay. So how do we do this? And it turns out that, so now the question is, how do we use vision and how do we use touch? So the vision you can see there. Now there's a hardware setup, which is that there's a hand which has got an object in it. And then there is a RGBD camera. This is an Intel RealSense camera, which is looking at that hand object combination. And then you get a signal, which is shown like this, the raw depth, the D channel of the RGBD. And then what we can do is we can segment out the object. And we segment out the object using SAM, segment anything. I mean, this is what computer vision can do for us today. If you have noticed robotics papers for decades, they usually use either green cloths or blue cloths or red cloths or whatever, depending on whether the experiment is being done at Berkeley or CMU. Okay, and enough of this, right? I mean, we should not need this, and computer vision can deliver this. We can do segmentation. So if you can segment out the object, that's great. Right, we can do that, and the depth image helps. And the hand, why is the hand not a problem? Well, it's your own hand, right? So you know the state of it. So proprioception can be used. It's very, very important. I hope that the field of vision and robotics grows together. And when you are doing research in this field, it's very important not to be just a vision chauvinist. We must use all the senses, which in this setting are the proprioception, knowledge of all the joint angles, touch, as well as vision. Okay, so we got the depth, and then there's a tactile image. So this is the image on one of those fingertips, and we have 4 of those fingertips. So each one of them has some image. Now this is going to, this pattern, this image encodes in some form where on the finger the contact is. Okay, so this is the setup, and let's see how it works. Okay, it looks a little bit clumsy because there are these cables from the sensor and so on, but you should trust me that this is rotation about the x-axis. Okay, and I can show you more examples where I mean it rotates about the y-axis and so forth. So we achieved our goal, which was that to be able to rotate about any axis. Okay, let me see if I can move this along a bit further. So this is still the rotating about the x-axis, but hopefully you saw that there are different objects being rotated with exactly the same policy. Okay. And this is something that people can't do readily. So now it's rotating about the y-axis and a different shaped object. And then this is z-axis, which is the easy case, which we have shown earlier. And this is some arbitrary axis. Okay. Okay, you got the demo. Okay, how do we train this? So it turned out that the same philosophy, which I showed earlier, it's called RMA, rapid motor adaptation, which we use for walking, applies equally well for dexterous manipulation. So first we train a policy using privileged information. So privileged information here is the shape of the object, and the shape of the object can be captured by a point cloud. In this case, the object that you are turning, you know, in simulation. So you have a point cloud for that object. You can run it through a PointNet encoder and it'll be fine. And the physics parameters are known, the mass, the friction, etc., etc. And then this privileged encoder compresses it down to a Z. And then there's a control policy which takes Z as input as well as the previous observations and actions, and it outputs an action 80, which is the desired joint angles. Okay, and you keep repeating this. Now at test time, you do not have access to the true shape of the object. How can you have the true shape of the object, the true point cloud of the object? You don't have that because all you have is an RGBD camera image, right? And you have a tactile signal. So the goal has to be that can we take the sequence of observations, in this case, which would be these RGBD images plus these tactile images, and from that predict this latent variable Z. And that's what we do at the bottom, what's called the visual tactile policy. So the Oracle policy has access to all this information in simulation, but in the real world, you won't know all that. You have to estimate it. You estimate it from your sensor observations, which are the RGBD camera plus the tactile sensor. And what we have is the sequence of those observations, and they go into this green box at the bottom called a visual tactile transformer. Of course, nowadays we have to use transformers, right? So, but we use that, and what it is trying to predict is the Z, for which we have the ground truth value from the upper policy. And now we've got it and we can run it. So we trained an Oracle policy in simulation, and then which includes object physical properties. The object shape is encoded in there, and then we can run it. Now, what do we do? How do we train? It's important to have a lot of variety in training. So the way you do this is that you take lots of object shapes, like ShapeNet kind of objects. For these, we have ground truth shape and point clouds, and then we use them at training time. And then at real time, what we're going to do is use vision and touch. And how does that work? Okay, so again, we must, in simulation, we can do the same thing, right? What we're going to do in real world. You know the hand, you know the object. And the goal is, because you'll see only the front of the object. With an RGBD camera, you see only the front of the object, and it's been segmented out using SAM. Now, from that front of the object, you will try to guess the whole object, but it will be an incomplete guess, and it's compressed down to this latent vector Z. It doesn't have to be a perfect reconstruction. And then for touch, what we have is that these fingertips are sensitive, and where you touch the object, there will be some impression created, which is shown in these images. And you do some low-level image processing, which essentially extracts the location of the touch. And then this goes into the transformer. So the transformer is getting the depth image from the RGBD sensor, and it's getting the point contacts on the fingers from this analysis. And then the transformer's job is to figure out from that the relevant latent. So these are experiments, and I want to show you what we have here. So there are 3 rows here. So the policy here, there's rotation about the x-axis, y-axis, and z-axis. So we could, generally speaking, we could do a good job on z-axis rotation, but we could not do a good job on x-axis rotation and y-axis rotation in the first row. So the first row is HORA, which is our previous policy, which did not have access to vision and touch. And you can see, for example, the time to failure on the x-axis is 0.52, right? For example, this Oracle policy does very well. Okay, so the numbers are much better. And then without shape, again, it declines. So it shows that shape plays an important role. So what are we saying? For very difficult dexterous manipulation tasks, knowing about the object shape matters. That's a summary of this. And that object shape is going to come from vision and touch. And here is more detailed stuff. So one is that transformers are better for this task than coordinates. I mean, we have seen that in many other applications. It's true here. And then there are if you look at the bottom block, you please don't try to read all those numbers, but the key ones are that higher is better. So like look at that 118.42 on in the left column. So that's the performance, meaning that it can rotate a lot, and that's great. That's with access to both vision and touch. And with only touch, you get 99. With only vision, you get 102. And with none of them, you get 79. So it's beautiful. From 80, you go to 100 or 99, depending on whether you use vision and touch. Using them together takes you to 110. So I have always had this debate with people about is touch necessary, is vision necessary? And this is a very conclusive proof for this task that both are necessary. And now we are able to do these tasks which we couldn't do before. And then it's also interesting to see where the benefits come. If you have a very simple object like a sphere, it turns out that everything works. You don't need any sensing. It's for these more complicated shapes that we get the benefits of touch and sensing. And those are shown here. So how much time do I have?
You have approximately 3 minutes.
Okay, well, I will use the 3 minutes. So, so our policy learns shape information from this visuotactile information. Okay, so this is, okay, that's a summary of this. And here is another experiment you can do, which is that this latent Z that is being acquired while you're rotating the object, this latent, we can try to run a decoder which says from this Z, what is the likely shape that you estimated. Okay, and that is quite revealing. If you look at the leftmost is the ground truth. Okay, so that's the object mesh. And what you find is that essentially as the representations in the columns on the right, they correspond to making use of the touch and vision information. And basically what you see is that the latents have captured some approximate nature of the shape. Okay. That's because you look at the rightmost column and it's pretty close to the leftmost column. But you captured that shape without in an implicit way. And this is, I think, very fundamental because to me, it shakes up my classical vision training. This is the Gibsonian view. The Gibsonian view is that we don't necessarily care about objective shape. We care about affordances. What is a shape? What we care about is how we interact with an object. And this is the implicit shape as inferred during this interaction task. Okay. And it's kind of an approximation to the objective shape, but it's not exactly the objective shape. So this is what we are led to. I mean, this is the paradigm of, it's also very active. The way vision and touch are operating is that you are getting the sensing while manipulating the object. So it is in the context of a task, and it is an active process of multiple images and touch impressions being collected and integrated into this. So what that means is that our classic obsession on very accurate 3D reconstructions or things like that are maybe pointless. I mean, it may not be necessary to do those kinds of classic reconstructions. And this is a lesson that I'm seeing across the board in areas of robotics that I have worked in. I started out in like 5-7 years ago. We started to work on navigation with Saurabh, and we found that the classic SLAM was not necessary. It actually missed out on essential aspects of the domain. It captured too much detail of unnecessary geometry and too little of the semantics. Then we started to work on walking, and again, we found that it is not necessary to reconstruct the terrain on which you walk. What you need is relevant information for the task. And then this is now a third such exercise, which is dexterous manipulation. Same thing. Okay, and that's where I want to end. And I view this as a paradigmatic example of how to approach dexterous manipulation in the future. There is lots of work to be done. I think it'll take decade or more. And it really requires the vision community to work together with the robotics community. And I also want to say with great pleasure, this is not going to be solved by ChatGPT. And I'll end here.
So while we switch to the next speaker, we probably have time for one question.
Yeah, Pietro.
I had a question.
Should I turn on the video or?
I think it's fine with the video.
Okay.
So can the people on Zoom confirm that they can hear us so that we're not talking to the void? Excellent. Thank you so much. So our next speaker is Vincent Lepetit. He is from École de Pons in Paris Tech. And so before that, he was at TU Graz. So he has done really a lot of amazing work across the across 3D. So including early work on detecting features and matching them, for which he won a Test of Time award at ECCV, as well as great work on understanding hands, understanding object pose, and understanding AR. And so it's a real great pleasure to hear about handling complex hand-object manipulations, which I know is something that all of us here are very interested to find out about. So thank you so much.
Thank you for the introduction, David. Okay, so let's start. So we'll just put things in context. I will start with pretty early work, so all the work we did on hand tracking. So I'm interested in 3D computer vision. And so something like 10 years ago, we started working on hand pose estimation. So that's now that looks like a very easy problem. So, but that was still a challenging problem at the time. So we had quite a lot of training data already. So, but the goal was to, what we wanted to do was to predict the 3D pose of hand. And you can see that it's a depth camera. So nowadays, it's something very easy. But at the time, it was almost enough to get a paper at CVPR. But so that was already a good start. But it was difficult to get anything better, so we could tune the parameters, the hyperparameters of your CNN and so on. It was still difficult to really improve the accuracy, just by tweaking the network that was not good enough. And then so we started to do something which I think is pretty general for all 3D pose estimation problems, and I will show it in the context of hand pose estimation, but very quickly, so as an introduction to the problem. So what we did was to introduce two additional networks. So there is a first network that generates an image. So that was not with diffusion. So that was with a standard CNN at the time. But the idea is, let's say that we have a first pose that is estimated by the first network. And then, so this pose is not completely perfect. And we train a second CNN to generate an image of the hand given the pose that we get as a first estimate. So what is interesting here, the first thing to realize is that we don't need additional data for training, so we can use exactly the same training data. It's just that we switch the input and the output. So we get an image which looks like that. So it's not perfect, but we don't really care. And then we have a third network that takes these two images. So the original input image, so that's actually a depth map, this rendered depth map, and then this network is trying to compare these two images. Okay, maybe I should replay the video. And this last network is trying to compare the two images and predict an update for the pose. So what happens here is that we take the input image, we predict a first pose. From this pose, we generate a new image, and this network is going to compare these two images and give us a delta pose, so an update for the pose. We can update the pose and then iterate, and usually in a few iterations, we converge to something which is better than with just the first network. So that was just an introduction to show what we were doing at the time. So in fact, that's this kind of things is pretty general. So it has been extended by different works. So DPIM, cozy pose, if you know the literature on 3D object pose estimation, and then something that we can apply to other problems. And then, so the next natural step was to consider problems where we would also consider an object which is manipulated by the hand. And then things started to be pretty much more difficult. So there was a fundamental problem in the sense that we needed training data. So that's everything was supervised, especially at the time. And then we realized that it's really difficult to get training data for this kind of problem. So that was, we started with depth maps because it's easier, and of course, so with color images, that's going to be even more difficult. So we had some heuristics to add rendering. So here, that's a very simple object. So that's a box added to rendered into real depth maps, but that was weird. So it was really difficult to get to generate a nice hand pose or nice grasping of the box by the hand. And actually, so we were not alone to have the problem. So at the time, so people were working into trying to generate images of hands and objects with some 3D annotation. So there were different solutions that were considered. So all these were interesting so far. So that's, I just put an example of this first-person hand action dataset. But they were using sensors, so you can see these little cables and sensors. That's nice. So that was working to get the 3D pose of the hand, but of course you can see the sensors in the images. So that's not necessarily very nice if you want to do computer vision. So there was this data set generating realistic images, but the images were realistic, but the 3D poses or the grasps were not necessarily very realistic. And there was this one which was actually very interesting. So the Obman data set. And the trick was that they reused a simulator from robotics, which was able to generate, okay, so that's to generate grasps like that. So that's something which is called power grasps, or static grasps. So that's something where the simulator guarantees that the robotic hand or the human hand really grasp the objects, but it's not really necessarily natural, so you cannot generate any poses like that. So that was very difficult to generate, to create training data for this kind of problems. And even if we are able to generate training data, maybe with synthetic images and so on, so we still have to get real images with 3D annotations if we want to do the evaluation correctly. So we really want to do the evaluation on real images, not synthetic images. So basically, we would like to have annotations like that. So the skeleton, the 3D pose for the hand, and the 3D pose for the object. So what can we do? So I really wanted to have these real images with 3D annotations. So the first option is to force the PhD students to do them, but they will probably end up killing me at some point. So I didn't go in this direction. You can ask a company to do it for you, or you can pay the company to do that for yourself. But it's still very difficult. So there is a lot of occlusions. It's not clear where the joints are. So it's really difficult to get 3D annotations in these real images. And another possibility would be to use markers, but we already saw that's not something that you want to have in real images. So that really bias the vision algorithms. So yeah, so somebody had to do this 3D annotation of real images. So we tried to develop a method being able to do that. So the general idea is to start for a 3D model of the hand, so something which is articulated. So if you work already in the area, you probably know the Mano model. So that's exactly what we needed for the project. Here we are going to assume that we have a 3D model of the object. So we took object from the YCB dataset. And now the goal is to annotate sequences that looks like that. And you can see, you already know that there are a lot of occlusions between, so the object is going to occlude some parts of the hand is going to occlude some part of the object, so that can be pretty tricky. So what we did was to shot video sequences, so that's something that looks like that. So actually we have several cameras that are synchronized, and we also have the depth maps to add more information, but the general idea is that we have a video stream or several video streams of the same action. We start from this hand model, the object model, and the starting idea is to so let's say that we have an initial estimate of the 3D pose of the hand, the 3D pose of the object, and we are going to do a non-realistic rendering. So that looks like that. So that's some sort of an image or class-coded image where we have the rendering of the hand in one class or one color, one class for the object and one class for the background. And the advantage of this synthetic or non-realistic rendering is that it's going to be much easier to compare the images with this rendering and the image. And to close the gap, we are going to use a segmentation. So we could use segment anything now, I guess. So that was a different model, but it doesn't matter. And so from this segmentation model, we get an image, so a class-coded image, which is similar, the same nature, and much easier to compare than the real and synthetic image. And then we can do pixel by pixel, so pixel to pixel comparison. So I say that we also have the depth maps. So it's not just the images, but also we do the comparison in depth. And then we can optimize the hand parameters, the object parameters, so that this image looks as much as possible to this one. So that's a typical strategy in computer vision. So that's called render and compare now. In the old days, that was called analysis by synthesis, and that's something which is very strong, very robust. We can do the same, of course, for all the images of the sequence. And since there is some continuity, we can add some regularization on the object and pose. So that's at the end we get a very big loss function that we can optimize over all the pose parameters for the hand, the object, over all the images. And again, yes, so that we have multiple cameras, so that add quite a lot of 3D geometry constraints. And we get something which is pretty accurate. So that's, and the advantage is now we do have an automatic method, and then it's almost only a matter of capturing sequences and run the method to get the annotations. And so from that, so we can get a lot of sequences that are annotated, because now that everything is automated. So that's called the HO3D dataset. And then so Shreyas, I don't know if Shreyas is here, but anyway, so that's the PhD student who was working on this project. So extended the method, but just by adding a second hand, and then it's really the same idea, but we can get these more complex manipulations with two hands and an object. Okay, and so since the annotations are automated, so we still need to do an evaluation of the quality of the accuracy of these annotations. And so basically, so since we have a point cloud, because we also have the several cameras, so several capture of the same scene, we get a point cloud. We look at where the joints of the hand should be. We click that manually, selected in a few frames or several frames, and then we can compare what the automated. we compare the automated method, so the annotations from the automated method with the annotations, the manual annotations, to get an idea of how good the automated annotations are. And so we get an error which is a few millimeters, which is actually pretty good. Okay, how much time do we have?
Yeah, 10 minutes.
10 minutes, okay. And so now we have a relatively slow method that is able to annotate sequences by using the temporal consistency and so on. And now we would like to have a fast inference of the pose of the hand and the object from a single image, and maybe just a single color image. So to do something like that. So these images are from our data set, and these images, so that's a data set from Meta, I think. And also, of course, we started using transformers. What is very challenging here is that if we have two hands, then it's very easy to make a mistake by confusing joints of one hand with the joints of the other hand. So they can look, all the joints look more or less the same. So that's, and plus there are some occlusions, so some joints are not visible in the images. And so to solve this challenge, so we have a method. So I will give the architecture in the next slide, but we have a method where we start by detecting the joints. So we get something that looks like that, in the sense that we detect most of the joints. So we don't, at this stage, we don't know which joint, which detection is correspond to which joint, but we get most of them. So we can still, at this stage, we can still miss some of them. We can still have false positives, so like this one, but it's already a good start. So we know more or less where the joints are, and then we have a second step where that sort out what is what, so which detection correspond to which joint. And so that's a good way to not to mess up too much, because then, so this second step is going to look at all the joints at the same time. And so, oops, So for the detection, so we use a unit, so something standard to get a heat map, and the local maximums correspond to the position of the joints. And then we use a transformer to take all these joints, and the transformer does its magic to identify the joints and to tell us also the 3D positions or the 3D location of the joints. And so if we want to estimate, to predict the pose of the objects, we can actually do something which is pretty similar by sampling points in the silhouette of the object, and it's really the same framework. So we'll not detail everything, but the transformer is going to also associate the points that correspond to the object. So first associate them correctly to the object, and then also predict the 3D pose. So it's really the same framework, the same transformer that predict the pose of the hands and the pose of the object. And just so some results on just 2 hands only, but with quite a lot of difficult interactions between the two hands. And here that's the same for the object. So here the model, so the architecture is trained for the objects. So it's not like we can take new objects. It has to be trained on these objects first. But we get something which is pretty reliable. And okay, so how much time?
7 minutes or so?
7 minutes. Okay. And so we can also analyze the attention used by the transformer to understand what the transformer does exactly. So for example, so this joint, so that's this joint for the left hand, which is occluded in this image. So it's not possible. So we do not see it in the image, but the transformer also use the detection of the other joints to predict the position of the joints, so correctly, so in 2D, but also in 3D. So we can see that the transformer uses the joints that are connected to the occluded joints to do this prediction. So it's does pretty clever things. And maybe so last work, which is going to be presented at CVPR. So that's at the main conference. So the next logical step now would be to reconstruct the 3D object. So with what I presented so far, we assume that we know the 3D object. We know everything, basically, the appearance, the 3D model. Now we would like to get a 3D model of the object. So just by manipulating, by showing to the camera the object in different positions, so different views. So it's not completely perfect, but that's a very difficult, that's a very tough problem. So especially because we reuse the sequences from the previous datasets that were not designed to do object scanning. So there are parts of the objects that are completely occluded, never seen by the camera. So that's where we have a lot of noise. So that's actually not a new problem. So object scanning, that's, I remember papers for quite a long time ago. But if we just look at the recent papers, so there was a paper at SIGGRAPH last year that was doing exactly the same thing, but they also use or consider these static grasps. So that means that the hand does not move with respect to the object. So basically you have to do motions like that were not natural at all. So you want to do more stuff, things like that to do the scanning. So exactly like in this video. And here that's actually much more challenging. So as a professor, so I wanted to use the hands to guide to first detect the hand, maybe predict the 3D pose of the hand, to use that as an input to the 3D reconstruction. But that's something which is still very challenging, because if you want to do this fine motion to rotate the object. That's something which is very difficult to capture. And at the end, so that sounds good on paper, but actually to make the things work, that's something which is still very difficult. So at the end, we end up completely discarding the hand, not really using the hands to get the 3D reconstruction. So we wanted to, okay, so we are going to use nerfs like everybody else. So especially because they can also capture the specularities of the objects. And so that's something that definitely works well. But for that, so we need the 3D pose. So in this case, so that's the 3D pose of the object with respect to the camera. And actually, once we have the 3D pose of the object, or the 3D poses for all the images, we get a very good reconstruction. So the nerf works very well. We can discard the background, we can discard the hand, run any nerf method on the using the object poses, and that works. We get something which is great. So actually, the challenge is really into getting the 3D pose of the object. So let's see. So if we consider a sequence that looks like that, we could run what we started doing is to optimize the parameters of the nerf, the parameters of the camera poses. But that never really worked. And if you have an experience, or if you already did 2D tracking or 3D tracking with objects, maybe you can realize that, so these kind of frames are very challenging. So in the sense that, so at the beginning of the sequence, we see quite a lot of the object. Suddenly we see only something which is very thin, and then a new part of the object that we have not seen so far. And these kind of sequences, they always happen in practice and are very challenging. So that here the tracking was always breaking at this point. And so there is a lot of tricks and a lot of ideas in the paper. We'll just show this part. So the idea was to segment the object and look at the local maximums and the local minimums of the object. And we get something like that. So we can see that that's a local minimum. That's where the object almost disappears, or is starting to, a lot of things are starting to disappear, and then new things are going to appear. That's a local maximum of the area of the object. And that's actually a good image for initializing the tracking. So the idea was to split the sequence into sequences based on these local minimums or local optimums of the area of the object, and then run the tracking on each segment independently. So starting from where the object is large, and then the object is going to disappear, or at least a lot of things are going to decrease. Then run an optimization of each segment individually, and then put everything all together. And then that's the kind of result. So again, it's not perfect, but that's some things without any prior. So it's just a 3D reconstruction from images. That's still a very challenging problem. And that's just a bunch of results. That's we can also capture some specularities of the object and deal with really complex manipulation of the objects. Okay, I will stop here. So that's again, so there is a lot of tricks, a lot of details that I didn't talk about this last work, but we have a poster on Thursday morning on this work. And I will end here. So all this work is mostly by Shreya, so who is not here apparently, but also in collaboration with people from TU Graz, and also Meta for the last work. Okay, thanks a lot.
Thank you so much for the wonderful talk. So while we're switching presenters, we probably have time for one question. Jim.
I have a question.
Yep.
2. Just do done. Please presenter view. All right, so they've got presenter view. All right, so can the people on Zoom please confirm that they can hear us? We only have the highest ones. All right, okay, cool. All right, excellent. So I'm very pleased to have Zikong Fan for our next speaker. So he's currently a PhD student at ETH, and before that, he was actually at UBC. So this is coming back for him. And he's done really, really cool work on understanding hands interacting with things. And so it's a great pleasure to hear you present your work for us. So please take it away.
Thank you, David, for the nice introduction. So I'm a PhD student, as the introduction. I'm working on hand interaction with different objects. So to start with my talk today, I want to motivate it with a hobby of mine, which is, okay. Okay, yeah, cooking. So I really like to cook in my daily life, and I really want to share my cooking tutorial to my nieces. But the problem is I live in Zurich, while my nieces actually lives in Vancouver. So it's a little bit hard for me to teach them how to cook on a video that I take by myself. So how about, okay. So cooking involves very complex hand interaction with objects. So we grasp food with our hands. We use two hands to coordinate when we cook food, and we use complex articulated tools during the cooking process. So how about we develop a vision system that takes a video of me cooking, and then I reconstruct both my hands and the object I'm interacting with from those videos. And maybe in the future, I can pass those 3D reconstruction to my niece so that they can learn to cook immersively in a VR headset or AR. So I hope that convinced you that we need to model hands in 3D, otherwise it won't be in this workshop. But there are also other more general applications for modeling 3D hand interactions. For example, in AR, VR, for dexterous manipulation for robotics hands, and also for human and robot collaborations. For example, in this paper from Sammy. However, reconstructing hand interaction from RGB images is a very challenging problem. First of all, the two hands' texture are very similar to each other, which means it creates ambiguity when we estimate the hand poses for interacting hands. And secondly, generalization is a challenging problem for hand pose estimation. Finally, our hands dexterously manipulates complex objects in our everyday life, and we use very complex tools. So to tackle the first problem of appearance ambiguity, we look at this image. The hand parts are very hard to recognize even for a human, unless we actually pay attention. It's even difficult when we don't have context, which can be created by occlusion when we manipulate with objects. So in this project, I worked on 3D interacting hand pose estimation. The goal of the project was, given an input image, we want to estimate the 3D joint locations for interacting hands. So I want to motivate the projects by a toy example of a very light touch interaction when two hands interact. So if we look at the index finger for the right hand, and we train a model that uses fully supervised data from interhand to estimate the 3D joints. You can see that the index finger of the right hand actually have an incorrect assignment to the incorrect hands. So we want to understand what is actually causing this issue for incorrect prediction, even for this very simple task for human. So the baseline network here is using a 2.5D representation with a Gaussian heat map to supervise, meaning that we can visualize the 2D prediction as a heat map. So here's the heat map for the prediction. So the plus here is indicating the predicted position for the 2D joints. And the cross here is actually indicating the ground truth position. So the ground truth and the predicted position are quite far away from each other. And you can also see that from the 2D heat map here, the network assigns a really high weight on the heat map on the incorrect joints. So how do we address this ambiguity issues when two hands interact? The key insight of our paper is that we need to construct a representation to model highly uncertain, to model the uncertainty when we recognize hand parts. And we can use those uncertainty estimates to then reason about hand semantics to help downstream post-estimation. So the main idea of the paper is that we first divide the hand topology into different parts based on the manual topology. And each part here is denoted by different color. We then, for a image backbone, given the image, we can extract a feature map, which is pretty standard in computer vision. And then for each grid in the feature map, we can estimate a probability distribution of what parts that grid is corresponding to for the hands. So now if we perform this estimate for all the grid in the volume, then we have a separate volume containing semantic information of our hand parts. So if we use this probability estimate for downstream post-estimation, you can see results like this, where the baseline is on the left and our prediction is on the right. So our prediction actually is quite robust to cases when the two hands start to interact strongly. So now we are trying to address the problem of appearance ambiguity. A second challenge in hand post estimation is generalization. The reason is that when hand interacting in real life, the lighting condition is extremely challenging. They're very diverse lighting condition. Many different objects can also interact with the hand. So that also poses additional challenges. And lastly, the environment that we interact with are very diverse. A key observation of a paper here, TempClear, is that we have a lot of unlabeled videos on YouTube. We have very diverse background and hand interaction from those videos. So how about I leverage a lot of unlabeled videos for hand interaction and devise a self-supervised training loss such that we can do a pre-training on those unlabeled large-scale videos, and then do a fine-tuning on labeled images. So to put it more concrete, TempClear formulate around contrasted learning for hand post estimation. So in contrasted learning, so we define an image backbone, say function f, that takes an image x, and then map it to a latent pose v. And the latent features are corresponding to provide information for downstream post estimation. So in contrasted learning, we need to design a triplet for images, meaning that we need to define x0, x plus, and x minus, meaning that x naught is the reference image, x plus is a positive sample of the image relative to the reference, and the x minus is a negative sample. So to put it more concretely, we want to train a neural network such that the distances between the positive sample to the reference image will be closer than the distance between the negative sample to the reference image. So on the right, you can see the x naught and x plus, they have very similar hand poses. And we want to train them such a way that the latent space, they will be closer together from the one of the reference image to the negative sample. So now the next question is, given a enabled video from the internet, for example, how can we choose a triplet of such for the contrasted learning loss? So our key insight here is that hand poses that are closer in time in the video, they are more likely to be similar in terms of hand poses. So to put it more concrete, the x naught reference image will be more likely to be similar to x plus, which is an image that is closer in time, than x minus, which is further away in time. So if we perform a contrasted learning on video choosing these triplets, here are the results that we can see on unseen data sets. So on the right is showing TempClear, our results prediction. And in the middle, we are showing without a TempClear pre-training loss. So the prediction is more noisy without TempClear prior. We also show results on 100 days of hand, which has more diverse settings. So we try to adjust appearance ambiguity. We also adjust generalization. But the fact is, we humans don't actually just grasp objects. We have very dexterous two-hand manipulation with objects, and we use very complex tools. So for example, in this case, the person is cutting with a scissor for the haircut, and which require two-hand coordination. And we need to also model articulation. So the problem is that there's no such data set with accurate 3D annotation for both two hands and also articulated objects. So in this project of the CVPR, we introduced a data set called Arctic, which capture two hands jointly interacting with articulated objects. So here I'm showing a footage of the Arctic data sets. So note that the hand is actually, ground truth is actually rendered on the image. So the person is not wearing a white glove. And also the object is not purple, it's actually the 3D ground truth. We also capture the full body motion for this interaction. So just want to make a distinction between grasping and dexterous manipulation. On the left, we are showing a sequence, the ground truth and the RGB video of the interaction that is trapped by our data set. On the right, we are showing the hand and object contact that is very diverse. Here we show more 3D ground truth for the data set. You can see in the bottom, there's a sequence that is quite interesting where our subject actually almost dropped the object in our capture setup, but we are actually able to capture that very fast motion of object dropping. So our data set has 8 allocentric views and 1 egocentric views. And all those 9 views are synchronized and calibrated with the ground truth. Just to provide a little bit summary on the Arctic data set, we have 3D annotation for simple X, manual, and objects. We also have 2.1 million RGB images from videos. We capture articulated object with 1 degree of articulation, which is shown on the right. And we focus on dexterous manipulation beyond grasping. To outline our setup, we use a marker-based motion capture system. So we put markers on the subject and also the object with the egocentric camera. And you can see the markers on the hands and also on the object are only 1.5 millimeter in radius. So they are quite small. And when the image is captured and we scale to a neural network input, they will be barely visible. And on the right is showing we are using 54 motion capture camera to eliminate the hand and object occlusion, which is quite challenging for constructing a good data set. In here, we are showing the captured 3D mocap data we projected on the RGB image. And so the white dots are actually the tracked mocap location. They are not actually the marker texture. So if we take the hand poses of Arctic and also existing data sets, we can perform a t-SNE 2D clustering for hand poses to investigate the clustering of the poses. So you can see that the Arctic data set, which is shown in blue dots here, has more diversity in the t-SNE clustering, indicating diversity in hand poses. So because we capture both hand and object, we can compute the binary contact between hand and object, and we can integrate all the contact between hand and objects for hand and object separately. So you can see here the hotter region for the hand represent a more frequently contacted region, while the lighter or cooler regions actually representing less frequently in contact region. So for example, in this case, compared to grab, our wrist, the palm region for the hand is more spread out in the indicating by the yellow and greenish color here. So that indicates the diverse hand and object contact in our data sets. Below, we show the contact region for the object that we captured. So we define 2 tasks in Arctic. One task is called consistent motion reconstruction. Another task is called interaction field estimation. So for the reconstruction task, given a monocular video, we want to reconstruct the 3D geometry of both hand and articulate the object in 3D for every single frame. But we want the reconstruction to be consistent. What we mean by that is illustrated by this small example of a person opening a microwave door. So you can see on the bottom, that is a zoom in view. So the person is actually not in maintain constant contact with the microwave door in this model prediction. So this is what we mean by consistency. Because in real life, when we open a microwave door, we don't lose contact with the object. Otherwise, it's not physically plausible. So here we show some qualitative results for the reconstruction to show the feasibility of the task. And we also show the failure case of our baseline because there's a lot of future work can be done. So first failure case is that the object can be jitter in the prediction, because especially during highly dexterous manipulation by hands. A second failure case is the imperfect 2D alignment when we have the estimation. And lastly it's about consistency in time. So you can see the left hand is not always in contact with the laptop cover, but in the video it actually is. So there's a lot of those challenges we need to address as a community. So we pose a new challenge in currently we are accepting submissions. So we have an Arctic challenge for this motion reconstruction task and in ICCB. So a second task I want to introduce with Arctic is called interaction field estimation, which takes as the input a monocular video, and we want to estimate an interaction field for both the left hand and the right hand for every frame. To motivate this, I want to state that contact is a very important prior from the community because we've been using it for a lot of applications. For example, for reconstruction and motion generation. However, right now, the contact representation that's being used is mainly about binary contact estimation. For example, in this case, the hand is grasping an object, and the contact estimator will estimate a binary contact where on the hand vertices, whether it's in contact with an object or not. But binary contact may not be feasible for bimanual manipulation tasks because not all the hands are always in contact with the object, but they can in close proximity with the object. So we need a more generalized notion of contact in this two-hand space, which is what we call the interaction field estimation in our paper. So the main idea of the interaction field is giving an input. We want to estimate for each hand vertex the closest distance to the object surface, and vice versa from the object to the hand. So here we visualize those distances between hand and object as a heat map. And you can see the right hand here is in contact with the handlebar, which means the interaction field is light up on the object because it's very close to a hand. And while the hand is fingertips are close to the object, so it's brighter in the fingertips. And we can also do this in two hands because two hands. Yes, so if we visualize this interaction field as a video for the right hand, you can see when the two hands are not exactly in contact with the object, we still have a notion of contact or distance. And I hope that this representation can be useful for the community for downstream reconstruction tasks. So here to show the feasibility of the task. So the left here is showing the prediction from the baseline network on the left hand compared to the ground truth. On the right here, we're also showing for the right hand. So the ground truth and prediction correlate to each other. So we have introduced these two tasks for Arctic, but I think there's a lot of other tasks can be enabled by using our Arctic dataset, for example, generations. For example, in the literature, we have maybe 3 categories so far about hand and object motion generation. So the first category is a static generation. So given an object mass, you generate the hand that grabs the object. A second category is hand motion generation. For example, you have this object on the table, you try to pick it up. And the last category is a full body motion generation using this pickup motion. Compared to existing dataset, Arctic capture object articulation, and we also capture full body for the human. And our manipulation is not only for grasping, we are for dexterous manipulation. So potentially one can generalize those tasks to Arctic in this more generalized setting. And lastly, I want to note that there's a really great work community in articulated object pose estimation. So they have a model that actually estimate the object pose from depth images. But the problem is that when we interact with objects only move because there's human actuating the object. So I feel like Arctic may be a useful asset for future development for this community using a depth map that we capture. So we capture the 3D surface of the human, and you can render those depth map for this human and articulated object from depth map estimation task. Okay, so summarize the take-home messages. Two-hand interaction is very ambiguous, and you can disambiguate it with a path segmentation representation. Secondly, in the wild, generalization for hand pose is difficult, and you can use TempClear, which leverage a unlabeled video datasets, and just have a time-constructed learning strategy to help generalization. And lastly, we introduced a generalized contact representation co-interaction field for two-hand interaction. And Arctic can be used for a lot of downstream tasks. I would like to thank my collaborators, some of them are in this room, for all the feedback they provide me, and also my awesome supervisors, Omar and Michael. And finally, this is the information page listing all the ICCV conversation, the code, and all the projects that I've talked about today, and also the AIT viewer, which is awesome for visualizing 3D data for hand, which is shown on the right. My post-processing is in here.
Thank you so much for showing off such amazing work. We have time for some questions from the audience.
Yeah, so basically the idea is that you have a video of hand interaction. So if two hands are very close in the temporal, like time step, for example. Yes. So in this illustration, actually, is very close frame, but in our paper, we basically, yeah, we refer to, yeah.
Do you have a plan on language translation to like caption language?
Yeah, so the question is whether I have an idea for putting language into Arctic. So I actually have this idea as well, but it's not on my priority right now. But what one can do is, for example, you can annotate very simple atomic actions for interaction. And that can potentially help for generating human motion condition on language. I think that would be a pretty interesting direction. I think for adding more object to our data set, it's a orthogonal direction to our focus. So we're mainly focusing on understanding the relationship between the hand and the object in interaction. So I would say if you are more interested in more diverse objects, I think the HOI 4D dataset will be more suitable in that setting. So they have a lot of diverse objects, and while we're focusing on dexterous manipulation.
I don't think the paper you put much on like personal diversity using the same tool.
I think like really depending on the individual for the manipulation. Like some subjects are actually PhDs in our lab, and they have really creative way to manipulate with objects. Like for also other subjects are from outside of the lab, so they can some even try to squeeze the ketchup bottle that we have, but our mesh is rigid. So it really depending on the individual, but we only have 11 subjects in this case. So in terms of diversity, I think one would require to capture more subjects in this setting. Yeah, so the question is about soft objects capturing with hands, right? So I think it's a really good direction in this hand-object interaction. But the problem right now for capturing soft object is a hand occlusion. So like even if I hold a cup, like most of the cup will be occluded by my hand. So as Vincent mentioned, there's in their lab, when the hand is grasping each object, the occlusion will be an issue for the object geometry. So I would say at this point, capturing soft tissue object is quite difficult, even with a really proper hand scanner setup. I think the difficulty for soft object is because of the degree of freedom that you are tracking. Yeah. Thank you. So can you rephrase the question a little bit? What do you mean by specialized representation for graphs? Yeah, so you're referring to the template paper. Yeah. Yeah, so the idea of the clear paper is on the assumption that the hand, if they're closer, the poses will be more similar. So, and we perform a constructed learning training for this setting so that the closer hands will be closer in the embedding space. And that's the main idea. So did I answer your question?
Well, if there are no more questions, then let's thank the speaker again. All right, so we're going to do a little tech switcheroo. So those on Zoom, hold on for a little bit.
Can you hear us? Inter?
Yes, I'm here.
Inter, are you ready?
Okay, yes. Can you see my slides?
Yes, we can.
Okay. Sorry. Hello everyone. My name is Yunze Liu, and I'm a PhD student under the supervision of Professor Li Yi. It's my honor to present on the topic of 4D perception. Today, besides of the HY 4D dataset, I will discuss our explanation of backbone design and the 4D pre-training techniques. The first paper I will introduce is the
You can make
primitive.
your slides full screen. That would be great.
Sorry, I will.
Can you make your slides full screen?
You can't see my slides, right?
No, not now. Okay, yeah, it shows up. Perfect.
Okay, sorry for the delay. Okay, I will continue.
Hello, Yunze, are you still there? Yeah, we can start with the next one. So we can continue in the next. We can start with the second one. Jai Chen, from Peking University. Jai, are you online?
Oh, hi. Can you hear me?
Yes, we do.
Okay. So let me share my slides. Oh, I'm sorry. I had to. Oh, I have to quit my Zoom first and reconnect.
All right. Let's see. Maybe we can come back next. So we can maybe move on to the next speaker first. So Yuze, are you online?
Yes, I'm online. Can you hear me?
Yes, we can hear you. Are you ready to go first?
Oh, great. Yeah. Maybe let me try to share my screen here. Yes. Let me share my screen. Can you see my screen?
Yes.
Okay. Let me. Oh, sorry. Where is my play button? Okay. Oh, okay. Can you see my slides?
Yes, we can.
Oh, great. Yeah, maybe we can move on. So hello, everyone. I'm Yuzhe from UC San Diego. Yeah, so today I'm very excited to be here to share with my recent some work about vision-based robot teleoperation from hand detection. So I think everyone here already gets to know a lot of things about hand and object and all this perception algorithms. So with all these algorithms, can we ask the questions how to really utilize this a very exciting hand perception algorithm for robotics? So here I will give you an introduction. So today I will introduce the vision-based teleoperation. So what is the vision-based teleoperation? Basically here is a human, we call that pilot, to receive, there's a camera to capture the human hand, and then this using the algorithms, this hand pose detection will be converted to the control command for the robot, and then we can control a robot based on the human hand. So let's see an example here. So with this vision-based teleoperation, we can easily control a robot in a simulator to achieve some task, as you can see here. So I'm moving my hand in front of a camera, and then I can like control a robot hand inside the simulator to open a door. Yeah, similarly, this vision-based teleoperation can also apply to real robots. As you can see here, I'm moving my hand, and also which can control a robot hand in front of me to, yeah, including both the robot arm and the robot hand. Yeah, so yeah, we can get an intuitive mapping from the human motion to the robot motion to control the robot in an intuitive way. Yeah, so here I want to introduce our work, which is accepted by RSS. We build a general vision-based teleoperation system that can be used to teleop a lot of different robots, and the different hand, and also to achieve this kind of vision-based teleoperation task. Yeah, and many of my collaborators are here in this CVPR workshop. So basically, we want to build a general purpose teleoperation system with this advanced perception algorithms. So our teleoperations can work in different places, including different simulators and different real-world robots. So in order to build this system, we introduced several techniques to facilitate this vision-based teleoperation system. So first, we're trying to estimate the wrist motion from RGB only. So different from the maybe the general hand pose detection problem. So in teleoperations, we only focus on the relative motion of the human hand, as you can see here. So as long as we can get the relative human hand motion, we know how to control the robot. And also, if we want to retarget the motion from human to different robot hands, so that we can command the robot in an intuitive way. With these two technology, we can enable some very convenient features of this teleoperation. The first feature is calibration free. So which means that we do not need to calibrate the camera. We can place a camera everywhere since we only requires the relative motion. As you can see here, I do not to do any like extrinsic calibration between the camera and the robot. I can even place the camera right inside my hand, and then we can perform the teleoperation task. These features come from the relative wrist pose detection I just introduced above. Also, it can also enable the collision-free with the robot motion. Although the robot will follow the motion of my hand. However, if I want to collide with the robot deliberately, it will not listen to me since the robot do not want to hurt itself. Also, with this teleoperation, we can also even teleoperate to play a piano inside as a game. Also, yeah, like you can see here. And also, we can trying to use this teleoperation system to achieve some tasks in the real world. Yeah, this is a very challenging task actually, from both perception perspective and control perspective. Yeah, and also like, yeah, this is maybe a simpler, yeah, to using the motion followed by human to apply some manipulation task. Yeah, and this system is very easy to use. Actually, there's a lot of researchers here that can use this. Oh, sorry. Yeah, so different researchers here can use this teleoperation system to control the robot and to achieve some task. And one of the users showing the video are actually in person in this CVPR workshop, and thanks to him, Reihan. Yeah, and thanks to this vision-based teleoperation system, we can do some very interesting downstream applications. For example, the behavior cloning, which is a very common algorithm in the reinforcement learning community. So with this vision-based teleoperations, we can collect some demonstrations using the human hand motion to guide the robot to do some tasks like this one. Yeah, as you can see, by utilizing the demonstration collected by this teleoperating system, we can train our policy to achieve these tasks. Okay, that's all. Thank you. Yeah, thank you. Is there any question here?
Okay, in the meantime, when we are switching the presenter, maybe we can take one question for each.
Hi, yeah, very interesting. I'm just wondering, you said about being very quick. Children purpose is 26. I was wondering if you make use of the intrinsic methods of the camera or is the calibration free, as in, you know, would you be able to switch out the sensor you're using for an arbitrary when you find it in the hand to work?
I'm so sorry, actually, I cannot hear the question clearly. I'm wondering that, is it possible to repeat this question? Maybe near the speaker. I mean.
Yeah. I think it's easiest.
Hello.
Hi.
Can you repeat the question?
Oh yeah, sorry. So you speak about it being calibration free. Is that
yes?
Is that both extrinsic and intrinsic calibration, or is that just the extrinsic calibration, as in knowing the camera position in world space, or does it also work without knowing the intrinsic properties of the sensor?
Oh, that's a good question. So actually, what we require is only the FOV of the camera. So, but common camera like RealSense or your web camera on your MacBook has a relative fixed FOV. As long as we can get a rough value of the camera FOV, we can get it down. So for extrinsic parameters, we do not require that. So in conclusion, we only need the FOV in the intrinsic parameter in a rough value. For example, if the intrinsic is if the FOV is 650, as long as you can estimate it as 600, it can works. Yeah. And actually, this value can be easily acquired by just Google that. Yeah, you can Google the FOV of RealSense, Kinect, or any web camera easily. Yeah, you do not need to perform this intrinsic calibration by yourself.
Oh, fantastic. Thank you.
All right, our next speaker is Wei from CMU. So please take it away.
Screen, 1 second.
Hello everyone. My name is Yufei, and I'm going to present affordance diffusion, and this is a joint work with Xueting, Abhinav, Shalini, Stan, Jiaming, Shubham, and Sivei. So here's the problem with we want to solve. Given an RGB object image, we want to predict how would a human interact with it in the form of a 3D hand pose. While many previous work have tackled a similar problem that predict hand poses from a 3D object mesh. But this method will require a full object 3D mesh, which are quite hard to get from a single view. And another line of work takes in an RGB image and predict some representation of the interactions, such as the heat map, key points, the graph type, or the trajectories. These are just partial information about the predicted interactions, in the sense that we still don't know how to place our finger around the object. Then what could be the other approaches? And in our work, the key idea is to leverage the recent success in the image synthesis community. And we found that this can serve as a shortcut to get the 3D predictions. So more concretely, given an object image, we propose to first synthesize an image of a hand holding that object, from which 3D poses can be directly reconstructed. And multiple graphs can be sampled from our model, like we show here. So how do we first synthesize the HOI image? So our key idea is to factorize this to two steps: where and how to interact. So the where step will focus on the possible the spatial arrangement, like grasping from the right or grasping from the left. And the how step will focus on the local shape, like how the finger articulates around the object. And these two steps are connected by the layout, which is the mask that you see here. The layout are parameterized by 5 numbers, 2 for location, 2 for orientation, and 1 for size. And these 5 numbers can be transformed into a 2D masks. We use a diffusion model to generate the layout. In the early stage, the predictions can be far away from the object because they are noisy. And we refine the prediction by concat the predicted mask with the input and feed them again through the layout net. Now, when we have the predicted layout as a mask, we then want to hallucinate the appearance. So the appearance should respect the layout in the sense that within the masks, the model should hallucinate the finger articulation and the skin color and so on. And outside of the masks, the model should preserve the object identity. So you may notice that it shares the similar priors with an impending model, which is in fact what we did here. So we fine-tune an impending model to learn faster. Next, to get the 3D pose from it, we just use an off-the-shelf hand pose reconstruction, which is French mocap here. Since the images are realistic, we can get a reasonable 3D pose from it. Now, let me show you 3 samples drawn from the model. And the samples are different in terms of the layout, some hand approach from the left and some from the right. And they are also different in the articulation, like how the finger places around the handles. And note that we don't hard code right hand or left hand, but the model have to figure out by itself that the right hand are more plausible when you approach from the right, and vice versa. So how do we train the system? So we just want to tell the model, here is the object image, and here is how it looks when a human grasps it. So we need the pixel aligned training pairs. So how do we get the training pairs in scale? So we propose an automated approach that can scale up, which means we first find frames where hands are in contact with the object, and then we segment out the hand region and remove it by painting techniques. So since we know the ground truth mask, we can calculate the layout parameters of it. And we train our system on HOI 4D dataset only. And we show some results on the novel instances. And I have to say that the scenes do appear in the training set because there are only 4 scenes in the whole dataset. But surprisingly, what we found that is the system would channelize well to novel scenes like the Epic Kitchens dataset without any fine tuning. And the scenes are more cluttered and the lightings are more complicated, as you see here. Now, let us compare with the method that directly predict 3D poses. So GANHAM is a feed-forward approach. Some predictions are good, but some fails. And post-diffusion is a baseline that we implemented. We diffuse a 3D hand pose instead of a 2D layout mask. Since we allow the model to look at the input and predictions more than once, it works better than the GAN-hand. And here's our model. Remember, we synthesize the images first. And you can see some results are even better, like the laptop that's shown on the top. So you may feel the performance boost is not so much, but actually the boost is more clear in the out-of-domain test set. When the scene becomes more cluttered, as we show from top to bottom, direct 3D predictions, whether it's one step or multi-step, tends to fail badly. But our model still managed to output some reasonable 3D hand poses. Now we will compare the end-to-end synthesis. Sometimes the baseline just fail to draw a hand, and some other hand, they fail to generate hands in contact with the object. And also the numbers kind of stays the same. Beyond the better performance, and I want to argue that these two-step approach can offer more control over the synthesis. And this control can allow for many applications, as I will show next. First of all, we can replace the layout net with the user input. So the generated image will respect the given layout. And when the user said to approach from the right, they tend to grasp the handles. And when they approach from the left, they tend to grasp the mug body. And also, the layout net can also be constrained on the given locations and figure out the sizes and the approaching directions on its own. This also means that now we can reuse all of the previous work that predicts heat map or key points, and we can take their outputs and predict the complementary information about how to grasp. Now, let us resample a key point from the heat map, and our method can generate another set of outputs. To predict on scenes, we can simply crop out the object, and we constrain on the size of the hand, such that the generated hand will appear about the same size. That's all. And we have our code online, and the poster is on Thursday afternoon. Thank you for your attention.
We have data coming up next. So in the meantime, we can take one question for debate.
You can ask for help. So, did you observe that the generated hand sometimes doesn't look like a hand because that's typically a problem with diffusion models? And my follow-up question to is, have you tried to fix that because you have this mocap thing because you know that it should fit the mask or like the finger should match or something like that to make sure the diffusion model can be guided?
I will say that you already answered your question. Like I will give the same answer as yours actually. Yeah, so we actually feel that by fine-tuning on the hand-object connections, right now the model can already outperform the quality of the hand the model that hasn't been trained on hand-object connections only. And I think the problem is the reason is that since we feed the model just with more training data, and also we crop out the object, and the hand will actually take up more pixels in the whole frame, and that's will make the model perform better. Thanks.
Right. Our next speaker is Sandak from University of Michigan. So Sandak, take it away.
Hey, everyone. Hey, everyone. Sorry. Wait, okay. Hey, everyone. My name is Dan Shan. Today I'm going to talk about the project towards a richer 2D understanding of hands at scale. It's a joint work with Tianyi, Ida, Richard, and David. So previously, we have this hand object detection system trained on the 100 days of hands dataset, which can detect hands and its in-contact objects. For example, here both hands are interacting with the same bag here. This system has been widely used in action recognition, interactive object understanding, and robotics manipulation learning tasks. But this detection model is focusing on bounding box. The location information is still coarse, and we want to make it to be more precise. Here comes Visor. Visor selects frames and annotate objects masks for all active objects for each action clip. And in Visor, for each hand, we annotate the hand and its in-contact object relation. Then we extend the previous detection system to also predict the segmentations. We are looking forward to more competitive methods. Now the HOS challenge is one of the new applications challenge now, and we are looking for your participation. From 100 days of hands to Visor, we are able to get more detailed pixel level information, but there is still more to explore. For example, there are hand grasps and also the object types. Is an object and tool that can be used by a hand, and also how it can be used. There are more hand object configurations too, not only the one hand, one object interactions. By manual manipulation is getting more and more attention, and there are still more information there to be explored. So here we are proposing new days, a new diverse data set along with a detection system that will give us more HOI information. Our goal here is to provide a simple and easily extended model for the community to build up on. First, let's take a look at what the new system can do. This is what we already get, the hand box and the in-contact object box. Visor provides us with manual mask labels, but that's only on applications data. Now with the power of SIM, we can get very high quality mask annotations on more diverse data by querying bounding boxes. These SIM masks can be served as pseudo ground truths for our training. What's more, here we define our graph types. So graphs has been started for a long time. And given the flexibility of hands, we still do not have a grasp category that covers all the nuances and easy to use. Here we follow the Kalkowski, and we mainly distinguish non-prehensile versus prehensile, which means that it's whether the hand is holding things, power or precision, which depends on the power needs to grasp the object, and also prismatic versus circular, which is about the shape of the hand when you grasp the object. Beyond, objects are also being used for different purposes. For object usage, we define the fine-grained contact. We distinguish whether it is a tool object or a container and how it is being used. We find that tool objects are very interesting, but have not get enough attention in our community. Our system can detect if there is a second object in contact with the tool using the same reasoning. So to build such a system that can provide all of the above information and with high generation ability, we combined 3 existing data sets, which are interactions, visor, and COCO. Besides that, we also collect more video data from YouTube, and we note it as new video. Each data set has its own speciality, capturing different scenes, various kinds of object and object sizes from different perspectives. Combining all of them together makes a more diverse data set. It's worth noting that all of the image data in our data set has Creative Commons and with face redacted and minors removed. We also experiment the model on Eagle4D, and it shows its great zero-shot generalization ability on Eagle4D data. So here is the result trained and tested on new days. It performs really well, and the model performed very strong on Eagle4D too. Because Eagle4D does not provide all the labels here, we can only evaluate on hand and side. And after fine-tuning, the performance even got improved. And here are also some figures of results run on Eagle4D data. Our method is actually very simple. It's an extension to mask our CNN with extra outputs from the ROI port feature using MLPs. We noticed that the association between hand and object is very challenging, especially there are multiple people and multiple hands in the image. Distinct from the previous methods, we improved the association by predicting on pairs of ROI port features. Here is an example output from the previous model. You can see the detection and association is run here. And yeah, here is because of the occlusion, it makes the task very hard. With the new interaction association technologies and the association performance got improved a lot. And the overall performance is also much better than the previous one. So what actually more exciting is what kind of applications this system can enable. The first one we explored is retrieving hand configurations. So for example, here, by setting constraints on hands and objects, we can retrieve this kind of one hand using a tool interacting with a second object, and the other hand also contact with the second object directly configuration. So in this example, it is one hand holding the pot, and the other hand is holding the specular and stir the things in the pot. Yeah, this kind of configuration is very interesting. And you may be curious, here we use this kind of configuration on pot and specular, but what are other situations that this kind of configuration will be used? here are more examples we retrieved from the dataset. You can see there are one hand holding the pillar and the other hand peels a lemon, which is the first example on the top left. And on the bottom left, it is actually one hand holding a cup, and the other hand is stir something in the cup, and so on and so on. We can find all these kind of configurations in a large scale data set. Yeah, as mentioned, that is one kind of configuration. Actually, there are more interesting ones you can explore. For example, the very busy one, one hand may be in contact with the tool in contact with the second object, the other hand is as the same. Hand tool object, this is kind of configuration can also be retrieved from the data set. And also with the grasp prediction itself might be not accurate, since the grasp may fall between two categories and may cause ambiguities. But actually the ranking of the grasp probability is more useful. Thinking about keeping the top ranked grasp, we can get diverse and natural graphs from for each type from the internet data. This can help us to get useful data for some specific graphs you want for your task. And here are examples of 4 top ranked graphs or different types. This is maybe very small. Here is a zoomed view. Each one is a typical representation of each graph type. So in summary, by getting more HY information from 2D, our system can enable more interesting applications even in 2D, 3D, or 4D. And also it can help 4D HOI analysis. And that's all for the presentation. Our new days are currently in beta version and looking for testers. If you are interested in, please let us know. Thank you.
The speaker, and we can take a few questions.
More stats about like for example, how much percentage of the handout detections have this full end object, like it's give us a flavor about like how complicated the handout.
Okay, that is a good question. We do not have the kind of like percentage numbers ready, but there are actually a lot of configurations we can set and we can use our to retrieve. It depends on kind of what configuration you want. For example, the one hand tool object, the other hand tool object is more rare in the dataset, and I think one hand one object is the most common one. It depends on kind of like the complexity of the configurations. Yeah, that makes sense. Okay.
Cool. Yeah, so let's follow up with virtual detectors. So Inza, are you online?
Yes, my network seems fine now. I will try to share my screen. Okay, can you see my slides? And is everything goes well?
Yeah, it works fine.
Oh, perfect, great. Okay, I will continue. I will first introduce the paper, Primitive Point Transformer for Long-Term 4D point cloud video understanding. Processing point cloud videos is quite challenging task for machines in 2 aspects. The first one is effectiveness. Effectiveness refers to capture long-term spatial temporal information, and the efficiency refers to process point cloud videos with limited computing resources. And our work focuses on these 2 aspects. We found that the existing methods are neither effective nor efficient enough. First, they are not efficient enough to support long sequences due to memory limitation. Most methods can only process videos with maximum length of 3 frames, while others can boost up to 30 frames. Second, take people transformer as example. It is not effective enough. We remove the transformer model in the people transformer that fills features temporarily and compare it with the original version. As shown in the figure, without long-term temporal support, performance of people transformer drops very little. So to balance efficiency and effectiveness, we draw inspiration from geometry community and propose using primitive plans as the middle level representations to process point cloud videos. As shown in figure, different color indicates different primitives. After primitive fitting, points belongs to the same plan are clustered. So why primitive plans? Compared with raw points, primitive plans is more compact while keeps a relatively precise description of 3D geometry. In this fashion, primitive plans implies coherent geometric features and potential to build a hierarchical structure. Second, unlike dynamic points, they tend to be much more stable and consistent across different frames. And we can see the figure that the results of primitive fitting are very consistent across different frames. So using primitive plans to model the long-term context, not only is the need to directly deal with the huge number of raw points, but also facilitate long-term feature association. So our method improves effectiveness by building a hierarchical structure based on the primitive plans. 2 modules are introduced, the intra-primitive point transformer and primitive transformer. On the lower level, the intra-primitive point transformer restricts the communication of the point within each primitive region. Point fills features with neighbors in the same primitive. And on the upper level, primitive features are aggregated from points, and the intra-primitive transformers perform self-attention across different primitives. Compared with a flattened global transformer, such design is more friendly to optimization and effective in the in feature extraction. To support long-term video understanding efficiently, we introduce memory pool. Primitive features of different frames across the entire videos are pre-computed and stored in the memory pool. Specifically, we pre-train a 3D point feature learner to solve the task of interest just from every single frame, such as semantic segmentation. And point-wise max pooling is adopted for each primitive region. So the memory pool is maintained in an offline manner and contain primitive level representations, which is expressive and memory efficient. With the hierarchical structure and the offline memory pool, our method not only improves effectiveness, but also can realize high efficiency. So we perform a throughout evaluation on semantic segmentation and action recognition, and shows that our method is able to outperform previous method significantly. So the second paper I've introduced is complete to partial 4D distillation for self-supervised point cloud sequence representation learning. For 4D data, it's easy to collect, but expensive and difficult to annotate in large scale with fine details. As a result, there's a strong need for leveraging a large number of unlabeled 4D sequences. Self-supervised representation learning has shown its effectiveness in a wide range of fields. Therefore, we aim to fill in the absence of self-supervised point cloud sequence representation learning in this work. After unsupervised pre-training, we can fine-tune on the 4D downstream tasks, and we expect to get a performance improvement. Although 4D representation learning seems to be a straightforward extension of 3D, it's quite challenging to learn 4D representations in a self-supervised manner, because sorry, my network seems not well. Okay, is everything okay?
Yes.
Thank you. I will continue from this slide. So from the I will continue to explain this slide. As I mentioned, also the 4D representation learning seems to be a straightforward extension of 3D, but it is quite challenging to learn 4D representation because 4D representation needs to unify the geometry and motion information in a synergetic way. For the geometric aspect, the 4D representation learner needs to understand 3D geometry in a dynamic context. From the motion aspect, a 4D representation learner needs to understand motion in the 3D space. So to address the above challenge, we examine the nature of the 4D dynamic point cloud sequences and draw two main observations. First, most of the point cloud sequences have the same underlying 3D content with an optimal dynamic motion. So the better motion understanding helps aggregate partial observation to form the complete geometry understanding. Second, geometric correspondence across time could help estimate the relative motion between two frames. So the core is the synergetic nature of the geometry and the motion. So based on this, we developed a complete to partial 4D distillation method named C2P. Given a point cloud sequence, which we call it the complete sequence, we first sample a natural camera trajectory and generate a sequence of the partial view by reprojecting the input point cloud to these camera views. After this, the partial view sequences are fed to the student network, and the complete point cloud sequences are fed to the teacher network. Note that we use an asymmetric teacher-student network to perform 4D knowledge distillation in a better and more stable way. Finally, the knowledge from the teacher network within a time window is distilled into the features of the corresponding frame extracted by the student network. This not only makes the student learn geometric completeness, but also capture the motion information from the spatial temporal context. And our experience shows that our method outperforms the training from scratch and the existing pre-training method such as video MAE. Finally, I believe that the continued exploration of 4D perception will lead to even more exciting development and have the profound impact on a wide range of fields such as robotics and augmented reality. So that's all. Thank you for your attention.
Thank you, Yunze. So in the interest of time, let's move on to our last student speaker, Jiayi. Jiayi, are you online?
Yeah. Can you hear me?
Yes, we can.
Okay. Let me share the slides. Wait a second. Can you see the slides?
Yes, perfect.
Okay. So let me start my talk. Hi, everyone. I'm Jiayi Chen from Professor He Wang's lab at Peking University. In this talk, I will introduce our work tracking and reconstructing hand-object interactions from point cloud sequence in the wild. This work is accepted by AAAI 2023 as an oral presentation. Understanding HOI is an important vision task and has a lot of applications such as VR, AR, imitation learning, etc. However, understanding HOI can be difficult due to the heavy occlusion between hand and object, and it becomes more challenging for data in the wild, namely novel hand, novel object, and novel interactions. Here we show some example works on HOI. Those works rarely tackle in the wild setting and suffer from several limitations. First, most of them require to know the object shape for their pose estimation, which is not available in an unconstrained scenario. Second, most work take RGB as input and thus miss the informative depth information. Last but not least, most work focus on single frame setting and thus suffer from temporal inconsistency. To overcome the above three limitations, we formulate our task setting as below. Our input consists of three components. The first one is a point cloud sequence of segmented hand and object. The other two are initial hand pose and object pose with some noise. Our method will reconstruct the hand and object shape and track their pose. During test time, in the wild setting means we don't know the shape of hand and object, which greatly increases the difficulty of this task. Let's first look at some results of our method on the real-world dataset HO3D. We show the input point cloud and the output reconstruction in the camera view and the rotated view. We also overlay our output on the RGB image for visualization. Note that we don't use any real-world data for training, and we don't use the same object for training, and the network can generalize to the novel scene. On another real-world dataset, DXYZB, we can also get results with high-quality tracking and reconstruction. Our pipeline can run in 9 frames per second. In the following, I will introduce the main challenges in our task and the contribution of our work. The first challenge we met when we start this project is the lack of large-scale 3D datasets with full annotations. To mitigate this problem, our first contribution is to generate a realistic and diverse simulated dataset, which we call SimGrasp dataset. Here, the diverse means we use many objects in ShapeNet datasets, and the realistic means that we simulate the noise pattern of real sense camera in simulator. However, now we can directly use the newly released real-world dataset HOI-40, another work done by Professor Li Yi. Therefore, I will skip this part due to the time limit. In addition to the data challenge, learning-based hand tracking method is extremely underexplored. Previous learning-based works mainly focus on single-frame hand pose estimation, which cannot guarantee temporal pose coherence in tracking. What's more, they will suffer from the large ambiguity under the heavy occlusion in hand-object interactions. Our work, for the first time, proposed a point cloud-based hand pose tracking network, namely HandTrackNet, to tackle the above problems. The first contribution of our HandTrackNet is to improve the canonicalization technique. Previous work observed that hand global rotation can bring harm to the network training, so they proposed a method that first use PCA to compute an oriented bounding box of the input point cloud, and then use the B-box to canonicalize the hand. In this way, they can get rid of the influence of hand global rotation. However, this technique will fail in HOI scenario due to heavy occlusion. To overcome the problem of occlusion, we start with an observation that the hand palm can be seen as a rigid body when we move our hands. So we can define the global hand pose as the rigid transformation of the palm, which can be analytically solved given the 3D position of the palm joints JP. Then we can leverage a temporal continuity to canonicalize the input point cloud. Specifically, we can use the predicted hand joint positions from the last frame to solve its global hand pose. and use this pose to canonicalize the input point clouds as this frame. After canonicalization, to further improve temporal pose continuity, we propose to only regress the interframe residual motions of the hand joints, which is the regression learning. In summary, our proposed hand check net canonicalize both the input and output space, thus greatly facilitate the learning and the generalizability. Finally, in addition to dealing with hand, we need to check and reconstruct the object and make sure their shapes and motions are consistent. We thus propose a full pipeline that can online reconstruct and track both the hand and object. Here we walk you through our pipeline. Before tracking, our system needs an initialization phase at frame 0. During this phase, our goal is to get the initial shapes of hand and object. We use Mano to represent the reconstructed hand, which is a template-based parametric model that takes input pose code theta, shape code beta, and the output are hand mesh. To obtain the parameters of the hand template, we first use hand checknet to refine the initial noisy hand pose. Then we optimize the hand shape code beta to fit the Mano template to our predicted hand joints J0 pred. As for the object, we reconstruct it using the implicit representation SDF. We first canonicalize the object point cloud using the initial pose. Then we optimize the shape code of deep SDF to fit the canonicalized point cloud. After initialization, our system performs online pose tracking and reconstruction for the hand and object. For hand, at each frame, hand checknet outputs hand joint position JP pred. Then we use a MLP, which we call inverse kinematic network, to convert the joint position into hand pose code theta. We can also get the global hand pose as introduced in the canonicalization module. For object pose tracking, we simply perform online optimization based depth to SDF conformation. These two modules can run in parallel and reach a speed of more than 25 FPS. Finally, to enforce physical realness, we construct prior energy term about penetration and attraction using the post hand mesh and object SDF. We then refine the hand pose via optimization. Besides, we can also offline update hand and object shape every 10 frames, which further boosts the performance of both reconstruction and the tracking. Finally, we show some qualitative results. Compared to previous SOTA methods, we have the lowest mean per joint position error on both HO3D and DexYCB datasets. Compared to the SOTA point cloud-based object pose tracking method CAPTCHA, we have higher 5° 5 cm accuracy on both datasets. To conclude, in this work, we propose a large-scale, diverse, and realistic simulated dataset SimGrasp. We also propose the first point cloud-based hand tracking network, HandTrackNet, that outperforms previous works. Furthermore, we build an online system that jointly track and reconstruct hand-object interactions in the wild. Experiments show that our method achieves the highest performance on both HO3D and DexYCB datasets. We have released the code and data. Here is the link. Thanks for your attention.
Thank you, Jai. So let's move on to our keynote speakers. We have 3 excited keynote talks. The first one is from Mark Polarface. So let me introduce Mark. Mark Polarface is a professor of computer science at ETH Zurich and the director of Microsoft Mixed Reality and AI Lab in Zurich. where he works with a team of scientists and engineers to develop advanced perception capabilities for HoloLens and mixed reality. So Mark is best known for his work in 3D computer vision, having been the first to develop a software pipeline to automatically turn photographs into 3D models, and also work on robotics, graphics, and machine learning problems. Mark also has done work on real-time 3D scanning with mobile devices, a real-time pipeline for 3D reconstruction of cities from vehicle-mounted cameras, camera-based self-driving cars, and the first fully autonomous human-based drone. So we are very excited to have Mark with us today.
Is that here you actually feel transparent. You see the real world. You have peripheral vision. You can actually do things and walk around in the real world in the factory without being at risk, without this being kind of a problem of how you actually interact with the real world. So these type of devices I talk about here and that I'll show applications for, it's really about devices where the primary purpose is to actually work in the real world, where you want some layers of information added to the world, but what you really care about is to see the world and to do things actively, physically in the real world. Okay, so to state the difference between content-first devices and world-first devices. Okay. So to operate, there's a number of different things, a number of cameras I knew for tracking your motion, which is needed to place content in the context of the real physical world. There's a depth camera built in that's used both for doing 3D reconstruction of the environment, analyzing the environment, mapping out the environment, so that you can have the real elements and the virtual elements actually interact, you know, in a physically meaningful way. So if I place an object, it will sit on the existing objects, it will not fall through them, and so on. As a byproduct, you can kind of build full 3D models of the environment, but I'll skip that. Very importantly, we also leverage that depth camera to actually track the hands of the user and enable interactions, as you see here, interactions with virtual objects. In a sense, similar to how you would interact with real objects, because we track the hands, you can do that. But as I said, the scenario that I'll talk about here is actually about interactions with real world objects. We also have eye tracking built in, so essentially you also know where the person is looking, where they're paying attention, and so on. It's also used for calibration of display and a number of things like this that are actually very important for providing a good experience, but I won't go into detail there. So if we look at scenarios then for, where we try to then, what we're doing is trying from those sensor streams, either from just RGB video, or also we can also leverage those intermediate signals that come out of the HoloLens for APIs, which is eye tracking, the hand tracking. All of those signals can also be used for doing action recognition. So we'll talk about, we've been exploring both, and in particular, if you want to do things live on device, then being able to work from those mid-level signals, building on top of the existing APIs, allows you to have much more compact and smaller models, but both essentially can be done. This was the first work we did in the space. This was from RGB video to essentially do action understanding in the sense of a hand interacting with an object and performing some tasks. This is essentially this was published at CVPR a few years ago, CVPR 19. It was using a YOLO model to find the hand and the object. And then it had an RNN that was essentially stringing together detections across frames to come to a simple model that would essentially, from a video, as you see on the left here, you can essentially infer the action, 3D interpretation of the action, both the hand grasp as well, the hand action and grasp and so on pose, as well as the object pose and what they are doing, what the interaction actually is like, opening or closing, or etc. Okay. We continued that. We set up a relatively large data set, both with egocentric vision and allocentric sensors, so Kinects that are mounted around the environment and record all of this to build ground truth. So we had data set, benchmark, and then also develop baseline algorithms. In particular, what we did was, our previous work, we also extended to now two-hand interactions, so two-handed interactions with objects. And you see some of that data set visualized here. And you can find more information at the link provided there. Then if we look at, now to give you an impression of the type of things that you could do in an application. So I showed you before these applications where you have a tutorial, a mixed reality tutorial that tells you step by step how to perform a certain procedure. Think of maintenance or this or that. Here during COVID, the kind of machines that we had at our disposal, or that Bura, who was doing this work, was doing at home. He had a printer, and so that's where we, that's the kind of example we took. But essentially, it has a six-step procedure here, and as he's doing this, the computer can, the algorithm can automatically follow along the different steps. This works with these typical examples where the person is actually learning to go through a specific procedure. If the algorithms, currently actually in HoloLens today, if you use the application called Guides, where you get this step-by-step tutorial, currently HoloLens just displays you the instructions. It doesn't actually know if you're following the instructions. So what this work is about actually being able to close the loop and have essentially the teacher also validate if the pupil is actually following the instructions. Okay, and so for example here, same thing, but person makes a mistake in the steps, so opens here, that's fine, then switches to the wrong step, then the device could intervene and essentially say, hey, you forgot a step, you should switch, and so on and so on. So you can actually also say you go through the tutorial, you learn it a few times, afterwards, you could do kind of a go blind through the tutorial, so not show the instructions anymore, validate if people have really remembered all the steps, and can essentially, you know, can graduate from the curriculum, essentially. Okay. Now, if you want to train from raw data, there's of course always issues of labeling a lot of data. This was some work we did with an intern, Jana Hassan at the time at the lab, who was essentially looking at, can we also, you know, only label a very small subset of the data, and then from that, you know, spread out to neighboring frames and somehow still get the value of all the data, but have mostly unsupervised data with just a few images being validated, leveraging photometric consistency and so on. So some optical flow and so on. So that's here quickly sketching the method, where essentially we have a presentation like this, and we end up having something like this here, where compared to 100% of the training data, we get qualitatively almost as good results with about 2.5% of the data hand labeled, and then can then train algorithms from that. But we can propagate the labeling essentially from a very small set of hand labeled, you know, data. Further in our pursuit of trying to, you know, go from a limited amount of labeled data to larger sets of data, we did some work here that was published last year at CVPR. That was from one reference image that is split in a number of different tasks, be able to have an unsupervised alignment of that data. So we label one sequence with different steps, and then we can, in an unsupervised way, temporally align other sequences that go through the same actions, so that we can essentially really expand the training data to all of these then unsupervised kind of additional data that we know they have the same, so very weakly labeled in the sense that we know they do the same action, they go through the same steps, but they might do that different rhythm from a different viewpoint, different, you know, with a lot of variations, but still manage to get alignment there. And here's something similar, but that works not on the raw data, but now on the intermediate signals, so on the actual skeleton. So we have here skeleton tracks, and then similarly there, we have an alignment. This was also published at CVPR last year. Then here I want to briefly also show some work that's here in this case, not so much about manipulating objects, although there are objects in this, but it's mostly about egocentric and also allocentric views to complement that. So the work is Ego Body, was published at ECCP last year, was really about understanding how people interact. And so you see the interaction from one point of view, you also see it from outside, from a third person point of view, and model that and model these interactions and where people are looking at. You have to gaze and see what they are doing and how they interact with other people. We'll actually, in some of the things I show later, we use some of this work also as a foundation for some of the things we do later. Then what are the places where all of this matters? Well, one example is in the medical domain for surgeons. This is work together with the hospital in Zurich. They are big fans of using augmented reality in surgery. You will see it switch back and forth between a cadaver experiment that you see sometimes, but also actually the real surgery. This was a world first of doing a particular type of spine surgery where they actually they fuse different vertebrae together, and they have to screw a metal plate attached to different vertebrae. And to do that, they need a metal bar that has the right shape that can, you know, essentially attach all of it. And so they use HoloLens as a way to do that feedback. That's just one example of this type of procedure. This was a success. The problem is this is actually the real surgery, so sorry for those that this might disturb, but essentially you have to press in this metal bar and it's better bent in the right shape, or you have to go back to the bench, bend it a bit more, try again, and so on. The key is here with mixed reality, we can actually reduce the time and the number of iterations you have to do to put it properly in the right shape and perform this procedure, which has obvious advantages for the patient in terms of time that the surgery takes, etc., etc. Okay, so in that space, in surgery, there's a lot of very fine hand-object interactions going on with the tools, for example. And so this work of one of my students, Jonas Hein, who's essentially working in this space, trying to see how good we can do the tracking from limited set of sensors, in particular here, the drill that's used in many of the proceedings. Let me skip for this. This is some of the latest effort there. Just wanted to visualize, to show you some visualization. We're also trying now to get full three-dimensional, actually four-dimensional captures of surgeries, as you see illustrated here. This is not a real surgery, of course. This is on a cadaver experiment, but really with the goal to be able to, in the future, capture these surgeries and be able to generate a curriculum so that people can experience this. Now, to make this as rich as possible, you also want to track all of the instruments, see what the person is doing, be able to add semantic annotation to what is going on. So here's some of the capture setup with essentially all of these fixed views with Kinects, and then on top of that, direct HoloLens views from the viewpoint of the different people involved in the surgery. And then here's another project. This is a project that we do between the Microsoft Lab and APFL, colleagues at APFL, which is essentially the same as ETH, but in Lausanne. And so the key purpose here is to, lots of people in this field have used kitchens as, good examples to do hand-object interactions and action recognition. Here we do the same, but with a different goal. The goal is really to be able to actually do functional measurements of neurological patients. So patients that maybe had an event that means that they lost some of their functionality in being able to do certain tasks. You want to measure that. Typically, you see as on the top here, they have very coarse ways to measure this, and you have to go into the doctor, they do a few tests, and they somehow score you on how well you are doing in evaluating, like, how much you are getting back your functions or, etc. The goal is to be able to translate that to a home environment, to be able to monitor people day in, day out, and have a much finer scale assessment of, how well they're doing, if they are regressing, if they are progressing, etc., etc. So in an intermediate step, we have an instrumented kitchen, highly instrumented kitchen, where we capture everything, and we're trying to, to see what we can do with that. So I'll show you a little bit of that data set here. So as I said, there's two key purposes here, both people, prosthetics, prosthetic patients, where you want to actually maybe also understand like the different motions and how you do things and leverage all these motion tracking and so on to figure out how to do new control algorithms and other things to make these methods, these prosthetics more effective. But on the other hand, for stroke patients, that's really where most of the focus is really being able to monitor in a more longitudinal way and a more permanent way, keep monitoring how well people are doing and at a fine scale track that. So the key is to really be able to measure that on a daily and unconstrained environment. Okay, for now, the environment is still very constrained. It's a highly instrumented kitchen. But essentially, this kitchen, so what you see here is the kitchen has 5 or 6 Kinects mounted all around, so 3D cameras with color and everything. It has also the person wears a HoloLens device, and so all of those sensors streams are also collected. And then actually also some of the tools are also instrumented. So in particular, the knife, that's one of the recurrent tools that's being used, actually has an IMU attached to it. And also some of the doors, kitchen doors and so on, like some of the plates also have sensors so that we know when they're open and closed and so on. So you see here some of the data actually. And so of course, from the point of view of HoloLens, all of the person's gaze is being recorded, the hand tracks, etc. are all being recorded. Here's a reconstruction of the context in which this is happening. But really, this is essentially the type of data that's being recorded. So you see there's essentially 9 views here, both an egocentric view as well as all of these additional fixed views. of the environment. You see here, it starts with the person reading the instructions, reading the recipe. So there's 5 different recipes. I'll show them later. 5 different recipes. They read the instructions. Essentially, each recipe, they get 1 hour to perform the recipe. So they will come in multiple times. Every time they come in for 1 hour, they put on the HoloLens, the recording is started, they read the instructions, and then they start preparing the recipe. They start preparing the food in essentially a real functional kitchen. And so you see them start here and do things. And so all of this recording from all those viewpoints. Here's like a second example of a person doing things in the kitchen. And so you see this very rich data set. It both has all of this raw data. It also has the gaze, the hand tracks, all of these instrumented tools. All of this gets recorded, is all synchronized, and is a pretty large data set. Here's essentially the tasks that they have to do. So they will start, first session, they will actually do an omelet. So that's the simpler one. This is when they still learn how to use the tools and find their way around the kitchen. Then they do a ratatouille. Then they do a risotto. So this is over several days and several sessions, right? So they only do 1 session at a time. Then they do a second time a ratatouille to also be able to measure actually how, how they differ from one session to the other. And then they finish with a pad thai recipe. And they can actually eat the food afterwards if they want to and take that home. So those are volunteers that are doing that. There's both patients and also a class of, comparison class of healthy people. So here's essentially some of those kind of, what people are doing to give you an idea a little bit from this first person point of view. They're going in the fridge and pick up stuff. They are cutting things, seasoning, cooking, put the pasta in and then clean afterwards. That's also part of the job, is actually to leave the kitchen in a clean state. Here's some other things. This is for, how people prepare the risotto. Just as an example. Some more things. And so as I said, like having the knife instrument is actually a quite nice additional modality for these things. So there's a full line view signal on the knife, which also allows you to detect when you hit the plate. It reads very nicely in the signals. Then also here a test with an amputee, so trying to see how people with only 1 arm, for example, can get things done in the kitchen. Have a better understanding of that is also something that's being measured here in this system.
Therefore, we introduce HoloAssist, captured by 350 unique instructor-performer pairs, offers 169 hours of data with 8 modalities and 2,243 sessions. HoloAssist features a 2-person collaboration scenario and can be used to situate AI assistants in the physical world.
Person do something and you record it. Here we actually have an interactive session. If you remember, one of the real applications that currently in the market is actually having a remote person help a local person to do a task. And in a sense, that help is also teaching the person in a sense how to do something. And so what we've done here is that scenario, we lifted out that scenario. So you have 2 people interacting. So you have a remote person. Actually, let me show this here. So you see we've done many different tasks with many different objects to manipulate with many different subjects across multiple countries. So it's, I think it was 350 unique instructor-performer pairs. We have 169 hours of video where we collected all 8 modalities. That's the RGB video stream, the depth video stream, the eye gaze, the hand tracking, also the speech, etc. So we have 8 modalities in total, all captured synchronously and together. And so the scenario is really the following.
HoloAssist adopts a novel interactive remote assistance scenario where the headset wearer, referred as performer, is completing different object-centric tasks. The captured data is sent in real time to a remote instructor who will watch the captured video from the performer's perspective and guide the performer as needed.
And essentially it's telling them everything what to do. Why this is really important is because we see this as a way to learn how people, how in an interactive session you teach another person how to do something. We believe it's much richer in many ways to go through an interactive scenario between two people, solving this task together. Then essentially a person just, as you've seen before, you get a recipe and you execute the recipe. What we wanted to learn here is also, okay, at what level do we have to explain things? With some people that already have some background and some expertise, you just give them a few high-level instructions and they're good to go. And then if you have, someone that's not familiar with the task, they make mistakes, you have to intervene and correct them, they have to stop, they have to redo. You have to start really specifying much more detailed instructions. And so what we're exploring in this is really these kind of multiple levels of instructions, trying to also automatically, our goal is to automatically start understanding what are the different levels of abstractions that we can use, and this kind of hierarchical nature of providing instructions to people, going from experts to naive users or to people that have really no clue, and where you have to kind of provide much more. And so in this interactive setting, we can discover essentially the different meaningful levels of interaction. And so that's what we're really trying with this. Okay, so you get things like this here.
The performer corrected the mistake and returned to the task.
The person doing so, we have annotated all of this, and so you get things. Okay, the person performs this correctly. Then there's an instruction coming from the remote person. The person makes a mistake, so they have to correct, and so on. So all of those interactions are labeled. So we both provide a full dialogue, annotated dialogue, but we also provide essentially the kind of the category of the interaction essentially. As you see illustrated here, of course, all of this with a full sensor, full sensor package of what's happening actually in the world. Okay, so that's an ongoing project that's currently that's not yet published. If people here are interested in doing similar things and you have your own projects where you'd like to do things like this, then HoloLens can be a great platform for that. There's actually a few different tools, so you can get access to all of these modalities, both the raw sensor data modalities, as well as then through APIs, be able to, to get access directly on device, live, to hand tracks, to eye gaze, to the position of the head, to the 3D of the environment, etc. All of those things are essentially accessible and can be collected. So the first link, HoloLens for tool for CV, is essentially something around research mode. Research mode gives you access to all of the raw sensor data. And then the second one is a link to PSI, stands for Platform for Situated Intelligence. You actually see it on the right here, kind of the announcement on Twitter at the time. So PSI is essentially a wrapper around this research mode and all of the other APIs, and in particular allows you to relatively easily from a HoloLens stream all of the relevant sensor streams live to a PC, where you can then run all of your favorite algorithms or just store the data to then later do things offline. So it makes it actually quite easy to do this, similar type of things to what we were doing. And so lots of that, lots of the projects were actually built on these tools here. Okay, and then maybe a last thing that's actually different. It's a bit of an advertisement for a talk here at the conference, but why I'm showing it here is because it's something that really is, let me actually start playing the video here. It's something that also really brings the semantic and the environment in the game, the objects that are in the environment, really enables to discover that. It's actually the combination of, large language models, embeddings, together with an image embedding, so Clip, but then with Song Yu, and this was actually his internship at Google, with Tom Frankhauser and the whole team there, where essentially, in addition, so we have the word embeddings connected to the image embeddings, which then in this work, we're also connected to 3D, to 3D point cloud embeddings, embeddings that we could derive from 3D point clouds. And so now if we have a new 3D point cloud, like the one you see here, you can actually use both the image embeddings, the ability to extract embeddings from images and from 3D point clouds to actually, place now a consensus embedding at every point in the scene. And once you've done that, so instead of just, having an RGB 3D color point cloud here, we actually, in addition to that, have, a full embedding associated with every point on the surface. And now we can ask open scene questions. So, we can solve tasks that are not being defined in advance, but we can ask open questions. Cook, for example, we say cook, then we get the word embedding for cook. We go on our model and we correlate that vector with all of the vectors, embedding vectors we have in the scene, and we see where the strongest response is. That's what you see highlighted here, right? And so you can ask all types of questions about function, about materials, about affordances, about specific instances. I think there was a Snoopy example before, etc. So all of those things, you can ask all types of questions to this model. These embeddings actually capture all of this. And so that's something, you know, I'm very excited about. I think there's lots of applications. Also, I hope that similar things would actually also translate back to object interactions and more video kind of scenarios for those things. Okay, and essentially I'll leave it at that. You know, you can do lots of things with these headsets. Lots of the things that were discussed at the workshop here today can really be, you know, have very meaningful applications in, you know, these type of mixed reality scenarios where you look at assisting people doing tasks, and therefore it's important to be able to close the loop on, you know, have the device that's supposed to assist you actually be able to follow along and understand what you're doing. Therefore, we need this kind of hand-object interaction and, you know, people working with tools and manipulating things in the environment. Okay, that's it.
Sorry for the interesting talk. So we can open up for a few questions. So I actually have one. So when the remote person provides the assistant to the headset user, how does it provide the input? So it looks like it's like in the form of like text. I'm wondering whether, you know, like there's like more ways to make this feedback more smooth or fluent. For example, maybe you can, you know, have the remote person also wear the headset and see the same thing and then track the hand and do things and maybe re-render that hand in the user's headset.
Yeah. Those are all very good questions. So indeed, in this work in HoloAssist, we limited ourselves to just voice interaction. So the person receives, you know, sees through the camera, you know, essentially this camera here that's mounted on the device, sees what the other person is seeing, hears what the person is saying, so the person can ask questions, the person on site. And essentially that's the only modality, the only input that we provide to the person. If you actually look at the product that's currently, so this is also connected to this product that I showed all the way at the beginning of the talk. This product is called Remote Assist. And it's actually the flagship application for HoloLens. It's what people actually today use HoloLens for the most. There, it's actually much richer, the interaction at this point. So you can actually, specifically, you can place, you know, when you provide information, what you actually do is provide, you can actually place information in 3D aligned to the world. So you can place an arrow, you know, this is the button you have to now, you know, press, or, you know, this is the thing that you have to do. You can place all these instructions as 3D holograms in the world in front of the person, and they're attached to the world. So there's a translation. The remote person clicks on an image, a frozen image, clicks on the image and says, you know, place a particular content, virtual content there. That gets translated to the 3D world in front of the person, and then you get a 3D world attached instruction. So it is actually much richer. In the real application today, you have a richer interaction. We felt here in what we were doing, this was not what we needed. But yes, this is actually important to have a really useful tool. You want to leverage the capabilities of this device to be a true mixed reality device and provide that experience to the person on site, you know, to fully help them. Yeah.
Any more questions?
The cartridge in the change example you showed, I was wondering whether that was like the online actually recognition system that was being run, and also what the application and they were providing the system or it's a system side.
That's a very good question. That particular video was done offline and was done on RGB data. So it was like, you know, you saw actually the bonding box and so on that found the hand and all this. So that one was not online. We have actually very similar things that we've even kind of, you know, tried out in the real applications online. When we don't work, that's the difference, where we don't work on raw data, but we work on actually the results of the hand tracking algorithms and so on that are built in HoloLens and are all available in real time. So on the eye gaze, the head tracking, and the hand tracking. So based on those signals, we can train, and there we can train with, you know, maybe 5 to 10 examples and fit, and this is a very low dimensional model because it doesn't have 1 million pixels as the input, but just a few kind of coordinates of your hand, just the joints and the eye gaze direction and this and that in context of the object of reference. And so in that case, we actually have models that run, in real time on device directly off of those, and it's very compact models. So we can do that, and because it's a constrained setup where it's just recognizing a few different activities, and you have actually very informative data, the hand tracks and so on, you don't need many examples to recognize those correctly and discriminate between the different steps. Because it's a closed world, you expect only these 5 different actions or so. And so that is actually relatively simple to do. So yeah.
All right, that's thanks, Mark, again. Our next speaker is Laurel Pinto. So let me introduce Laurel. Laurel is an assistant professor of computer science at NYU Current, working on problems in robotics and machine learning. He's part of the computational intelligence, learning, vision, and robotics group. His lab's goal is to get robots to generalize in depth in the diverse world we live in. So to this end, his research touches the area of robot learning, representation learning, reinforcement learning, and affordance robotics. We are very excited to have L'Oreal with us today. And,
hello, everyone, and thank you for the really nice introduction. Is it all good? Okay. Oh. All right. So, welcome everyone. Is here. Okay, perfect. Yeah. Yeah, all good. Okay, all good? Yeah. All right. So in today's talk, what I'll be going over is some recent work in my group on teaching robots how to interact with objects. And as the title is trying to suggest, I'll give you an offer of 3 lessons that we have learned in our work. I hope it will be valuable to you, even if you work on robots or even if you work on just understanding how human hands should interact with objects. So to start off, just to sort of impress upon you the fact of how difficult doing a dexterous manipulation task is, here is a fun example. So let's say you want to open a can. Here's a small clip of a person opening a can, right? It's quite simple. All of us are able to do this. All of us are able to do this task quite easily. But if you look at it closely, you will see that there's a large amount of intricacies needed to open this. You have to first locate the can, move your hand to the can, wrap your fingers around it, wriggle your index finger under the tab, and then apply just the right amount of pressure to lift it up, right? It's such an intricate task that we are able to do so easily. But what is, I think, even more interesting is that as humans, you can do a wide variety of these interesting tasks. And as a roboticist, it shows you how far away we are from trying to achieve human level dexterity. Okay, so in the goal of trying to solve this problem, there are many approaches in trying to build these type of robot models. Actually, let me. Hopefully you can see this slightly better. Okay, so there are many ways in which you can try to build a robot model. One strong way of doing this is what I like to call a nativist approach. So what you do over here is you, as a human engineer, try to take in as much prior knowledge about the world. So this can be in the form of a friction model or a dynamics model. Many of you have probably heard of using Ojoko, for instance. Or even as a human, you can try to create the entire scene, like where exactly all the desks are, all the shelves are. And after you have this, you can then optimize robot models on top of it. Now, this way of doing, or this way of creating a robot model is quite successful. If you see something like a backflipping Boston Dynamics robot or this OpenAI Rubik's Cube solving robot, all of these use these type of models, right? You have to create some sort of simulation of the world, solve things in that simulation, and then transfer it onto the real world. But it also sort of highlights why doing this type of nativist approach is hard, because you need to have this big team which can model the real world, solve things in the real world, and then figure out how to transfer it. And then when you have to solve a new problem, you have to redo this whole effort over and over again, right? Which is why if you look at the Sim2Real community, solving each and every task is a new paper, right? You solve cube rotation, it's a paper. You do a Rubik's Cube solving, it's a new paper, because doing each and every one of these tasks requires so much effort. Okay, so on the other hand, you can do something which I like to call a tabula rasa approach, where you assume that the robot starts off from scratch. You have no information about the world, and you just learn from lots and lots of data, right? This is something which, as a vision person, you probably have seen a lot of, where you take large amounts of data, train a model on the data, and then maybe if the model is not working as well, you go back to the world, get more data, and keep improving these models. So it's something which we have tried out in robotics as well. We have these efforts where we have looked at how to grasp objects by just trying, from random interactions, you can